everyone, how are we doing? My voice is a lot better now, so good. Might cough a tiny bit. The music's so low, my hair's going all crazy. Join on in. Who's all here? Say hey in the chat. We can't even hear the music. Oh my gosh. There we go. Music is now playing. Get my hair out of the way, disappear out of the way there. It's too early. It's 10 a.m. I erased Sloan. Oh yeah, I think I clicked him away, right? Sorry. Oh, you can't even see the code. There we go. I thought something was weird. I'll never erase Sloan again. Sloan, class president Sloan from the past right there. There we go. Sounds like good volume there. Olivia, good to see you. Boo, good to see you. Might still clear my throat a little bit. On the upswing, I think Wednesday, Thursday was like the worst, where I was like coughing the most at night. We wait like 2 minutes. I'm almost home from work. Yeah, Rachel, let's wait 2 minutes. 2 minutes sounds like a good... Bro, you ready? Watch this. Set a 2-minute timer. There we go. 2 minutes.
Counting down.
We'll wait 2 minutes right here, then we'll get started. So you'll hear the start of the Kahoot. Every once in a while, Brian might clear his throat. Not as much coughing. No COVID, I think. No temperature. So pretty good right there. Thank you, Rachel. I was trying to read the comment right there. I was like, you're Brian, but I can't even read. Yeah. Awesome. My hair is getting so long. I need to get it cut. Getting crazy. Everyone's like, bring back long hair, Brian. I don't know. Getting really, really long. Trying to work on the camera to make it look better. Just my hair looks crazy today. It's the way it's gonna be. It's the way it's gonna be. How's everyone doing? Everyone ready for the final? Got a lot of big questions on here, a lot of topics. No, bring back long hair, Brian. I'm gonna shave it all day. Today's like one of those wacky hair days. It's Wacky Wednesday. Where is... Like I haven't used this in like forever. On my button here. I was gonna say I was gonna go review 3. Hannah, good to see you here. Allison, good to see you. Reagan, good to see you. Good work. We have a total of 35 people in the Kahoot right now. I love when we have 100. Big early Sunday morning. Is it the optimum time for Kahoot? A lot of people watch the Kahoot review, so check out the Kahoot review later. But also check out review 3, which Brian typed it in wrong. So is this BAS or stat? This is stat 201 right now, and then we'll do BAS 320 next at about 11:30. Then we'll do BAS 474. So you can check out later in this review where we'll go into more topics. So lots of fun stuff. Gabriel, good to see you. We're gonna start here in just a moment. Literally seconds away from starting, literally 13 seconds. So if you don't get in right now, you can still join later. I call this Kahoot. No, I said reviewing for the final. Sometimes we get people who mess with us if we put Kahoot in the title because people search that on YouTube, so I don't put Kahoot in the title. Wow. Loud ringer. Oh my gosh. My little sister, she's 10, watched a lecture with me. Owen Tiny Brian absolutely loved it. Olivia, that's awesome. Shout outs to your sister, Olivia. So she says she wishes her school was like this. Well, awesome. Well, she can join it and tell her to grab her phone if she wants to play along. See if she beats you. Say, hey, grab your phone, play along if she's watching right now. See if she wins. This is, just learning stats, and anyone can play who wants. So even if you're a random person on the internet, now we can't give you prizes, it only goes out to the students, but you're free to play along with us right here and see if you win. I need some I'm ready's in the chat. We start these Kahoots, we say, I'm ready, I'm ready, I'm ready. Throws back to the references right there. Like SpongeBob. Yep, SpongeBob's been around since like 1999. So we got some I'm ready's in the chat. Here we go in 3, 2, 1. Almost 50 people in the Kahoot. Let's start. Here we go. Kelly's ready right there. Kylie's ready. First question of the day. Here we go. To test the mean, we use a sample size of 98 and a standard deviation of 2 and the mean of 3. Find the degrees of freedom. I can't even speak. Now this seems like a complex question, but this is a thing we need to memorize. It's also on the formula sheet. So if you notice, we are testing the mean. Now this is where, what are we doing? We are doing a t-test. And I'll give you a hint. I'm not quite blocking the answer, wink, wink, but I am partially blocking it. So you might be wondering, what in the heck, how do I even answer this question? There are 3 times we use degrees of freedom in the class. So if you get this wrong, don't worry, we're gonna tell you how to answer it. Amazing, wow. Wow. Is that my wow button right there? Wow. Should do that. I knocked off the camera apparently. So, wow. If anyone got this wrong, who wants to say the formula in the chat? Who wants to remind everybody of the formula? It was the wow. I like it. Who wants to explain the formula right now? I'm going to bring up a little Word document right here while we're talking. A lot of people are saying n-1. And so the keynote you want to have, we're going to talk about notes you need to write down while doing this right here. And of course, we got the cat named Quant in the background. He might make an appearance today. Long story about that. You have to be in our class to understand. Is a note to have, an amazing work. A t-test is a test on the what? Finish my sentence right here. A t-test is a test on the what? Something on the screen, it looks like. Oh, I know what that is. Wow. Okay. 2 seconds. It is this. That's what that was. A t-test is it's the light right there. It's a test on the mean. So we are testing the mean right there. A t-test is a test on the mean. So when we do this, and it can be called a one sample t-test, means we are testing one mean. Two sample t-test means we are testing the difference between, oh my gosh, it kind of knows it, two means. Does that make sense? If you do a two sample t-test, you are testing the difference between two means. Very important right there. The degrees of freedom for this are what? For the one sample t-test, everyone was saying it, and Cameron's saying Mr. T is mean. If you're doing drugs, that's how we remember it. T-tests are for the mean. The degrees of freedom for the one sample t-test are what? n-1. Now this is where we have a kind of way of remembering this one. If you are doing the two sample t-test, the degrees of freedom are what? The two sample t degrees of freedom are, and people are saying in the chat, they are too complicated. Because here are, so degrees of freedom, two sample t, too complicated. And the actual answer, if you want to really see it, let me disappear so you can actually read this. The actual answer is right here. That's not it. I'm trying to copy image. Copy image. I think I copied image address. So there it is right there. Here's the degrees of freedom formula. It's nothing fun right there. We use applets to solve it. You will not need to solve it on the test. We just mentioned sometimes, like a question could say it's too complicated. But notice what it uses. It uses S2. What is S sub 2 and N sub 2? I asked two questions there. Yeah, no thanks. I don't got time for that. What is S sub 2? The what of sample what? Like if you think about what is S sub 2. So we should know this notation. Like we should just know what these things are. That's the important things to know in this formula. Like what is S sub 1? What is N sub 1? What is S sub 2? Standard deviation of sample 1. Standard deviation of sample 2. Sample size of sample 1. Sample size of sample 2. So the N represents sample size, and the S represents technically sample standard deviation, but if we say of sample 2, we'll make that very clear. S and sigma are slightly different. Sigma is population standard deviation, where S is sample standard deviation. So you do not need to memorize this formula. And I guess we'll mention one last thing on here since we have mentioned degrees of freedom. Remember, it's congratulations if you aced the Kahoot, but I want to make sure you know the things for the test too. So we have the chi-squared test of independence. When do we use the chi-squared test of independence? To help me out right here, chi-squared test of independence. Test the relation, I don't know how to spell independence. Two categorical variable. Tests the relationship between two categorical variables. Amazing work right there. The chi-squared tests two categorical variables. Really fun thing with this, degrees of freedom are, and does anyone remember degrees of freedom? What are the degrees of freedom? See if they're independent, right? Yeah, nice job, Cameron, right there. The degrees of freedom are what? And they're on the formula sheet too if you want to just look, but it helps to kind of remember. Rows minus 1 times column minus 1. Nice job right there, Alexis. Rows minus 1 times columns minus 1. And an easy way to think about this is if you get a chi-squared, and we'll just quickly draw on right here, like let's do freshman, sophomore, junior, senior, and let's do handedness. So how many degrees of freedom are there with freshman, sophomore, junior, senior, and handedness? So we have right, left, ambidextrous, and freshman, sophomore, junior, senior. How many degrees of freedom are there? Ooh, look at all the answers we got. We got a lot of different answers in the chat. Who wants to show the formula? And Sarah, nice job right there. Sarah's got the answers right there. We're going to pin Sarah's message. Amazing work and good to see you there, Evan. Next question on the Kahoot coming up here in just a moment. Huge review right here on degrees of freedom and what these tests are. No worries. You did the L, yeah. So what we talked about is another technique of drawing where you delete one row and you delete one column. And then you can actually look at it and see the 6 degrees of freedom. Another thing we talk about too is you say, Brian, this has 3 rows and 4 columns. Drop one finger and you get 2 times 3. So do this nice and slowly. See if you can do small problems like this where you have a chi-squared and you can see there are 3 rows and 4 columns, 3 by 4, right? And Eleanor is shown in the chat right there. Drop your fingers or do the multiplication right there. 2 times 3, 6. Some of my favorite problems to do right here to find degrees of freedom with the chi-squared test. You just have to think how many rows and how many columns. But be very careful. Do not use the what's over here on the side. A huge mistake people make is they also use the what's, which are not levels to the categorical variable. A huge mistake people make. So the answer was 6 degrees of freedom. A huge mistake is people use the totals. Don't use those. Those are not groups. They're just aggregates on the side. They're the margins. Don't use the totals. You want to see there's 3 levels to handedness and 4 levels to class someone's in. So amazing work right there. Let's see who's on the leaderboard because, wow, we did a lot of review, degrees of freedom, and types of tests, and great answers on those questions. So the leaderboard right now, we got Stellar Ferret looking with those shades, pretty cool, and Wise Dingo, Caring Elephant, Brave Eagle, and Amusing Rabbit. Who do you think I'm voting for? Say it in the chat right here as we get to the next question. Who do you think I'm pulling for? You know me. There we go. Which is not a condition for the confidence interval for the difference between 2 means? The bunny, of course. So which of these is not a condition for the confidence interval for the difference between 2 means? So when we do conditions, I'm going to bring up a video here in the background. So we're going to plug videos and all this good stuff, giving you tips on what to do. I'm hoping people are like, I got this. Easy question, Brian. Whoops, I changed the font size. I don't like that. Okay, pretty good job. Pretty good job. As I try to find the video in the background. You ready? Here's what my class knows. Condition 1. What is condition 1? Go ahead and tell me condition 1 right here. What is condition 1? I need to know in the chat condition 1. Randomness. So when it comes to randomness means that, there it is from the videos. Randomness means that we take a random sample. So the first condition for all these tests is randomness, random right there. Whether we're doing a chi-square test of independence, 2 sample t, testing the mean, 1 t test right there, or the categorical proportion test. Brian's in the background right there, but this is me showing you visually. And you can take pictures. I'll disappear off the screen so you can screenshot this or write this down for practice. So the first condition is we take a random sample. Condition 2, what is condition 2? Which wasn't one of the choices, but should be on there. It's a weird condition about oversampling. There's a lot of theory behind it. I could get into it, but then people fall asleep, and I want to keep you awake. So it's the 10% condition. The second condition right here is 10%, which states you need to take less than 10% of the population. So if UT has 30,000 students, our sample size would have to be less than what? So this is, we run into problems theoretically with finite populations where oversampling can cause issues. If UT has 30,000 students, our sample of UT students would need to be, in great job, Boo, right there, 3,000 or less. Now you need to do what, which past Brian does not do. Before you continue on to the third condition, you need to do what? Put them in the chat right there. You know what you need to do. Alexis said you need to pause because the third condition will be based on the type of test you are doing. You have 3 routes to go for the third condition. Can anyone list all 3 routes for the third condition? This is a really good chance to see if you know like the 3 choices you'd have to choose between, because 2 of them we've been doing a lot. The last one was just added on with chapter 19. And it's kind of ambiguous what the third one would be for chapter 19, but because you could pick between the last 2 for chapter 19. Chapter 19 is right here on chi-squared. What are the conditions? See if you can list them for practice right now to see if you know them. Just see if you can list them. This is your time to practice. And see if you know the choices for the three. Success, failure, nearly normal, and Maywin. My gosh, Maywin, great job right there. Those are the three right there. And even in order. Success, failure for all the way on the very far side, which I disappear if I try to reach towards. The nearly normal for the what test. If you are doing nearly normal, it's for the what test. I'm leaving in advance here where I've written these things down. Nearly normal is for the what tests. Nearly normal is for the what tests. So when you're testing the mean, I like William right there. It's like, yeah, I got this down. When you're doing t-test, it's nearly normal. Success failure is when we have categorical data, and the t-test is for the mean. So when it's quantitative, we do t-test. Notice the Q up there for quantitative. And last but not least, expected cell counts are 5. I guess, did I say that here next? Yep, I do that one right there. Expected cell counts are greater than or equal to 5. I'll post this link here in a moment if you want to go back and review this. I'll also disappear off the screen so you can screenshot it, but I do suggest writing it down for practice. Now here's the thing, if you want to memorize this, the last 2 chapters in the class have an extra condition, or have 2 more conditions after the pause. However you want to remember it, there are 4 conditions to some tests. So if we are testing independent means, what would be the assumption or condition to test independent means? Which I'm talking about a 2-sample t-test to test to see if there's a difference between 2 independent means. Pretty much independent means. It's that this mean does not influence this mean. So we have right here the condition for means is that, and I'll write it out fully right there, each mean is independent of the other. What does that mean? It means, let's say I have class A and class B. Class A's grades do not influence class B grades. That's independent means. Dependent means would be, imagine you are doing SAT prep and they give you a test before you do the prep course and they give you a test after you do the prep course. Where do you think you would theoretically do better in a before and after scenario with SAT prep? When do you think you would theoretically do better if you took an SAT prep course and they do like a baseline start and afterwards and they compare the means? Exactly, you'd probably do better afterwards. Now you're not going to do, you don't know for certain, but your score afterwards would depend on where you started. So the mean of the score after, the mean people have after, if we took 100 people and looked at their mean after, would depend on their mean before. And that's dependent means, often called a paired t-test, which we're not doing this semester. So don't worry about a paired t-test, which doesn't have this condition, different test where we're not testing independent means. So we have to assume our means are independent, like we're testing group A versus group B, not like a before and after scenario where the after is going to be influenced by the before. Now the last condition right here for the chi-square test of independence could be called CC. Why might we call count data condition CC? Brian's like, yep, there you go. Why would we call the count data condition CC? Why would we call the count data condition CC? Kind of like QQ. And you can see up here, CC is written at the top of this. Well, the cell, it doesn't deal with the cell chi-square, it deals with 2 categorical variables. So count data means your X and your Y are categorical. Technically, it could be the first thing you check because you can't do it, you can't do the chi-square test of independence if you're not doing 2 categorical variables. So technically, it could be the first condition. If you're looking for this video and you want to watch it or anything else in this playlist, let me rebookmark this because now it has the playlist. Has anyone watched any of these videos here? Has anyone watched any of these videos? Sam? Has anyone watched any of these videos right here? Because I think these are some of the best walkthrough videos on each of them. I go through each test and I explain it, all the notation, do an example. Highly suggest these videos as your review videos. Also the speedrun videos, but these are going to walk through the conditions, the tests, what they're doing and why. So check those out, and this is your time to review with this video. Let's see who's on the leaderboard. Here we go. Wait, oh, it doesn't manipulate, it doesn't show. Stellar Ferret, great job right there. Amusing Rabbit going up in the lead. Balanced Sloth, Rapid Dolphin, Friendly Etch. I don't know how to say that. I don't know how to English. Continuing on, next question. When doing a 2-sample t-test, the variables will be what? This gets a lot of people. We already mentioned a 2-sample t-test just a second ago where I said we would compare Class A's grades versus Class B grades. If you think about that example, it will answer the question. We just did an example a moment ago where we did class A grades versus class B grades. Now, a lot of people think, and I have a feeling we're gonna see a lot of blue right here. Are we gonna see it? No, don't worry, that's usually what happens. Because quant, you'd be doing what? And this is good for tools and techniques questions. If you were doing 2 quantitative variables, you're not doing a 2-sample t-test. If you're doing 2 quantitative variables, you're not doing a 2-sample t-test. And let's draw this out right here. In the words of Full House, draw it out. So if you're doing 2 quantitative variables, you're not doing a 2-sample t-test. Really? Okay. What are you doing if you're doing 2 quantitative variables? If you're doing 2 quantitative variables, what are you doing? If you're doing 2 quantitative variables, you're doing regression. So that's regression. Write that down right there. That's regression. If you're doing a categorical variable, what are you doing? Not that many people answer cat. Exactly, be a scatter plot. Ooh, nice job. Great job, Sarah. Look at Sarah's pinned comment, which we're about to show. So if you're doing 2 categorical variables, you're doing what? You're doing chi-squared test of independence. And so 2 categorical variables would be chi-squared test of independence. And there we go right there. If you're doing 1 quantitative variable, you're doing a what? Now, you don't have to, some statisticians will be like, you don't have to do this. I'm like, well, we could do this then. If you're doing 1 quantitative variable, you're just doing what? If you're doing 1 quantitative variable, right? The answers above these. This is regression. This is chi-square. And this is, yep, you're doing box plots, histograms, and this is a t-test because you're testing 1 mean. Does that make sense? That is a t-test. And what does a 2-sample t-test mean? Remember, and I know those are medians, but we can still measure the mean of these groups, even though box plots do show this. What does a 2-sample t-test say that we are doing? Now, I know I'm kind of connecting medians. We'll pretend these are symmetric. The 2-sample t-test is when we're doing what? That's a 2-samp t. What does the 2-sample t-test say we are doing? And I'll write the variable types over here. Q, quantitative, and C-cat. Difference between 2 means. So a lot of people get caught off guard by this because they think, oh, t-tests are quantitative, but the t-test being quantitative only speaks to the what variable. The t-test being quantitative only speaks to the what variable. Since this is a t-test, it only means the what variable. The y variable is quantitative, the variable of interest. The t speaks to the y being quantitative, which usually catches people off guard, which I think has been a great question. Remember, QQ straight enough, no outliers, plot doesn't thicken is regression, so you have 2 quantitative variables. CC is count data, so we just kind of mentioned that with the conditions over there, and you can see the differences between these when we do 2 categorical variables. Yeah, this is like tools and techniques when we ask you what would you use and when. Like side-by-side box plots are used when you have a quantitative and categorical, quantitative y, categorical x. Mosaic plots are used for 2 categorical variables. Box plots and histograms on the far side are used for 1 quantitative variable, and a scatter plot is used for 2 quantitative variables right there. So this is a very good, and Moira in the chat. Everyone, you know what? Let's throw out 1,000,000 points for Moira. 1,000,000 for Moira. We've been going crazy. We got to have a big occasion to throw out some points. Moira right there, giving tons of help to students. Moira, I've heard so many amazing things. Students saying SI has helped them so much. So Moira, huge thank you right there. Really appreciate it. Good to see you in the chat. W for Moira in the chat right there. Let's head back right here and do the next question on the Kahoot. Where's the Kahoot? Here we go. Where's the leaderboard? Bunny, where you at? Bunny in 3rd place, hopping up 1 time each time right there. Stellar Ferret, Rapid Dolphin, still in the lead. Balanced Sloth and Lively Boa right there, looking like a bird with hearts on his head. Cool stuff. Next question, which is not a way to check the nearly normal. So nearly normal is sometimes really complex for people. And some of these are definitely teaching to the test moments. I'm like looking at these and being like, I've seen this one on the test, just saying. Thank you, Jennifer, right there, and thank you, Moira. So there are 3 ways. Look at it. Look at the histogram. Well, I left one off, didn't I? No, there's 3 ways, right? I thought there was a 4th. A lot of people got this right here. Why is a bar chart not a way? Jesse, good to see you. Skydiving with Jesse is here. Oh my gosh, we got everyone here. So thank you, Jesse, for showing up right here. So, you know, we'll drop 1 more million. We already destroyed the point scale, so if you're here, you get it. I appreciate it. So thank you. We'll be checking points at the end of the semester. We got Skydiving with Jesse here. Okay, so why are bar charts not a way to check the nearly normal? Voice, says Cameron. Why are bar charts not a way to check the nearly normal? Like, say it very clearly. Bar charts are used for what? And this goes back to the previous thing we were writing down. You might just want to append there. Remember, try to write a lot of this down with me. You can also screenshot what I do. And Sarah said it perfectly right there. Bar charts, and Olivia also. Bar charts are used for categorical data. So if you have one categorical variable, so if we go over here and we have a categorical variable of interest, you can make bars, and you can also make pies. So this is kind of our this is just what you could do with it. You're not going to make a bar. Well, you could make a bar and a pie, but there's kind of the things you could do with a categorical variable. If you just have a quantitative variable, you could have also made a histogram, which kind of looks like a bar chart. We're just drawing that below it right here to say we could have also made a histogram right there. And really, this page right here has most everything. And I should show this again. Where's the all graphics? It's over here. All graphics is right here. So here is where you see with a quantitative y variable. Let me show you this and take a screenshot. Yes, exactly, Cameron. Literally, this is the start of the semester where we said scatter plots and time plots are 2 quantitative variables, quantitative y, quantitative x. Histograms, box plots, stem and leaf, and dot plots are all just A. That's why the x is blank, because there's no x variable. And who feels like this graphic makes a lot more sense looking at this now? Bar charts for categorical, exactly. Thank you so much more right there. My wife wrote this down because her handwriting is a billion times better than mine. Bar charts are my favorite pie charts are my favorite bars. Our friend right there, Marshall Erickson, helping us out. So hopefully this makes a lot more sense with what you can do. Let me ask you, if you are in this region, what kind of test are you doing? It says side-by-side box plots. What kind, nice job right there. What kind of test are you doing in this region? Like if you said the test you would do in this region where I'm pointing my pen to, and look, it's a quantitative y of interest and a categorical x, 2 sample t-test. If you are in this region, what test are you doing? And look, you're in categorical. You see which way I'm pointing? It would go across over there to cat x, cat y. If you're in this region right here, what test are you doing? You're doing the chi-squared test of independence. Chi-squared test of independence. If you are in this region right here, quant, what are you doing? So if you're in this region, look to the center of my pen. That's the region we're pointing at. If you're in this region, quant, you have the visualization. You're doing regression. This is logistic regression, which is the logistic curve. So that's what you're doing in this region if you want, with a categorical y, quantitative x, and the x is through it because we don't do that in step 1. If you're doing right here just a categorical variable, what test are you doing right here? If you're in this region, what test are you doing right here? So look to the center of my pen. You're just doing a categorical y of interest. What test are you doing with a categorical variable? What test are you doing with a categorical variable? This is a really good review if you can do these things and write them down. When testing a categorical variable, we are doing a test on the what? Everyone's paused for a moment right here. This goes all the way back to the start of this semester, where you can do an interval for it. Not this semester, but the start of the 3rd test. Test on the proportion, great answer, Sarah, right there, a 1 proportion test right there. And then think over here, that's the proportion test. And then if you're doing histograms and box plot, just a histogram, just a box plot, this is a what? If you're doing just a quantitative y variable of interest, that is a what? 1 sample test on the mean, exactly. So amazing work understanding what tests to do in these regions. And I wish my wife and I had erased these and I could just flash over to that and show you all them, but try writing them down and know the conditions and then know what tests you're doing in those regions. So amazing work right there, great job. Continuing on, keep writing these things down. I know we're hitting you with a lot of knowledge and we're seeing what you know and don't know, so keep it up. Leaderboard, Stella Ferret, Rapid Dolphin, Amusing Rabbit. We're gonna go top 3 from now on. Balanced Sloth and Royal Lobster. Interesting name. Here we go, next question. A researcher wants to examine the true GPA of students at UT. What type of test will they use? Really good tools and techniques question right here. They want to examine the true GPA of students at the University of Tennessee. little bit of a tools and techniques question. So if you encounter a question like this, the first thing you want to do, great job Cameron right there, King Cameron level, I love it. If you encounter a question like this, the way to beat it is to write down the variable types. Really good work. What did you write down when solving this question? Remember, the way to beat these questions is to go to the question you're working on and see how many variables are there. Well, first off, how many variables are there in this question? Be careful. Nice job, Cameron. How many variables are there in this question? It's a little tricky, be careful. How many variables are there in this question? So the way to beat these, there's just one variable, just one. We're testing the mean, and then so we want to understand the true GPA, and so we're going to analyze one quantitative variable. So that would mean this is a quantitative Y variable of interest. Does that make sense? And then of students of the University of Tennessee is the what of what? Which the other one's the parameter. So, because we understand the true GPA of students from the University of Tennessee, the students of the University of Tennessee is not a second variable, it's just the what of what. So the students of the University of Tennessee is not a second variable, it's just the pop of interest, the population we're interested in. Great job right there, Lauren and Anna. That's the population of interest. It's not a variable, it's just the group we're interested in. And then the true GPA is the parameter of interest, the thing we want to understand. Be very careful with words like population parameter of interest, population parameter of interest. What is the only word that really matters in this phrase? Because that's a lot to think about. When we say population parameter of interest, the real word that matters in that whole thing right there is what? Be careful, it's a little tricky. That is correct, Maywin, right there. It's actually, what matters in this one is parameter. A little tricky right there. Because we're still just asking what's the parameter, but in long form speech, it would be population parameter of interest. Does that make sense? Because it's for the population, the thing we are interested in, what we are measuring. I know it's a lot and we should just say parameter, but this would be the thing we are measuring. And if we say population of interest, then that is going to be just the population right here, even though it says more. But does that make sense? Population of interest is that, it's just the population of interest. And then the parameter, population parameter of interest is going to be the true GPA. And that is the thing we are measuring and trying to understand, and it does have a truth. Does this make sense? I'm just trying to hopefully make sense of the word population and parameter. And sometimes we start to put them all together in one big phrase, and then knowing which one matters in the phrase is the tough part a lot of times. Because I've definitely said that and confused people. So no, don't worry if you got it wrong, because good practice. Statisticians talk weird sometimes. That's what we do. So nice job. Good job, Hannah, right there, and Lauren. Next, leaderboard. There we go. Amusing Rabbit still in third. Leaderboard staying pretty much the same, but don't worry. We got more questions. Great job, Stellar, Ferret, and Rapid Dolphin. Here we go. To examine the difference between GPAs of students and if they own a dog, what type of test will they use? Remember, once again, find the variables and then think about what tests we are doing. We're going to look at some test output here in a moment. We have until 11:30, so we'll probably even get to do some more. So when you hear regression, you should think two quantitative variables. When you hear chi-squared, you should think categorical. 2Q, CC. When you hear one sample t-test, you should think analyzing one mean. No, Cameron. I might know who you are now if you jump off the leaderboard. Two sample t should think quantitative Y, categorical X. And that's what this is, because let's look at it. Nice job. We're doing really well, and I think people are taking amazing notes, because you notice some of these are review questions. Because explain to me, put it in the chat like this for practice. Let's go, says Jackson. Y equals this and X equals this. You can do it as one phrase. Tell me in the chat what the variables are, and then it'll kind of make, or you can even put a Q and a C next to them. But tell me what the variables are. Great job, Rachel, right there. Tell me what the variables are. Y is quantitative and X is categorical, because we're seeing if someone owning a dog or not explains, there's the X of it, what their GPA is. And GPA is Y, and X is owning a dog or not. So that's categories. Do you own a dog? Yes or no. And then the Y variable being GPA is quantitative. So this makes it a two sample t-test. Check out earlier in the video, because we're kind of doing, if we do the first time of mentioning it, then we'll go more in depth. If we do it a second time, it's more of a review now to see if you can recall it. So we have to practice, we have to review, When you hear it multiple times, it makes sense. Now, I do want to mention this. If you didn't know this, you can actually test more than one mean, and that's going to be an ANOVA. So that's an analysis of variance between the groups, and that's called an ANOVA, which I wrote, which is an acronym, analysis of variance. So you can test more than one mean, or more than two means, and it's then called an ANOVA right there. And technically, a t-test is an ANOVA, so you see it in the jump output when you do a two-sample t-test, you still get the ANOVA. Don't worry about that for 201. It's just we have ways of doing bigger things. Next question, or leaderboard. Wait, no, oh, amusing rabbit, no! And my sad thing doesn't work anymore. Sad day that my sad button doesn't work. I'll have to fix that. Oh well, we'll check that out later. Stellar Ferret, Rapid Dolphin. Next question, here we go. Favorite restaurant versus living on or off campus, what test would we use? A lot of tools and techniques right here for you to consider. Favorite restaurant. And if you want to practice, tell me the conditions for this. So if you've already answered, write the conditions for this. Favorite restaurant versus living off campus. Sad Sunday, no. That's what today should be called, Sad Sundays. Nice job, Cameron, right there. That is kind of one of the conditions too, right? I think people are seeing the answer. This is the chi-squared test of independence. The chi-squared test of independence, because favorite restaurants, categorical, random, 10%, and pause is not a condition, but I do love that right there, Anna. I just want to make sure no one thinks the condition. I don't think you think it is. And then two categorical variables and expected cell counts greater than 5. Great job right there on the conditions. People practicing in the chat when you know the chi-squared test of independence. Random, 10%, expected cell, pause, expected cell counts greater than 5, and then two categorical variables. Really good practice right there. If there's 10 restaurants in if there's 10 restaurants in Knoxville, we choose between. And obviously on or off campus, nice job, Rachel. It's repetition, it's repetition, it's repetition. There's 10 restaurants and there's on or off campus. How many degrees of freedom would this test have? If there's 10 restaurants and there's on or off campus, how many degrees of freedom would this have? This is practice right here. Degrees of freedom review. 9, just like that. Boom. Because 10 minus 1 is 9, 2 minus 1 is 1. Boom. Olivia is showing it right there. Great job, Olivia. We're going to pin your message. Thank you so much, Olivia, for that practice right here. Showing how to do it. 10 minus 1 times 2 minus 1. Chi-squared is rows minus 1 times columns minus 1. If you notice, and Sarah's got the extra thing on there, so I'm going to pin Sarah's message. This is where you want to be at, where you get to a question where it asks, like, what are the degrees of freedom? You're like, done. 1 sample t n minus 1, 2 sample t, too complicated. Chi-squared, rows minus 1 times columns minus 1. We know degrees of freedom. If you're wondering, just to mention it, degrees of freedom tell you which shape of the distribution you are using. So when you're doing a t-test, the degrees of freedom show you the shape of the t. So take a look right here. With more degrees of freedom, it does become more normal. So you have to know the degrees of freedom for the chi or the t. And we could show it with the chi also. The chi has degrees of freedom, and it becomes more normal also, becomes less right skew. So when doing the t or the chi-squared, there are degrees of freedom. Finish my sentence. The blank curve does not have degrees of freedom. The blank curve, because there's just one of it, it's not a family of curves where we determine the shape of it based on degrees of freedom. The blank curve, the normal curve, does not have degrees of freedom. It's just the normal curve. That's why you don't have to figure out the z normal curve exactly. Great job, Olivia, Jackson, Anna right there. Really good practice. And degrees of freedom tell you the shape of the curve. So you need to know the degrees of freedom before doing your analysis. Great job, Eleonora. I'm so proud of my students. Like I feel like the knowledge we give you in this class is an actual applied knowledge of how to do these things and when to run what test. So if you're doing something, let me do this right before the next question. Has anyone used anything we've done all semester in another class, whether it be regression, 1 sample t-test, 2 sample t-test, chi-squared test of independence? Has anyone used any of these things? I am coughing a lot less. And if so, what? Thank you, Jesse, right there, and Hannah. That's what makes me proud right there, and Moira, yes. So this is stuff, information management right there, informational management. Yeah, it's stuff used throughout all different majors and all different degrees. It's data analytics. It's what we do. Next question. Which of the following is not a valid alternative hypothesis? Oh, this is an easy one. One of the easiest questions we could possibly have. I want to know what I teach students helps them in their career, helps them in their education. helps them as an individual. Things like that really make my day. Give me points. Let's find out who got those points. Who said a phrase? And that pretty much everyone got it. If you got this wrong, don't worry. Maybe you misclicked. Who said, I know, too easy, right? So who said a phrase, because this is alternative, and you said a phrase, something has the something. Because you're like, oh, the something has the something. And we'll talk about how to do this here in a second. The null has the equal sign. The null has the equal sign. We know that, and the alternative can be one of three things. It can be less than, greater than, or not equal to. And so who picks the alternative? This could maybe be a teaching the test moment. Who picks the sign of the alternative, the data or the researcher? Who picks the alternative? Do we look at the data and say, oh, it's less than, we should do that? It's the researcher's question, straight from the notes right there, the researcher question. Whatever the researcher is analyzing, the researcher picks it based on what they want to analyze before collecting data, because it's their alternative hypothesis based on what they are wondering. Then they collect data and see if there's evidence for their alternative. So it's kind of interesting because we don't look at the data first. We first come up with an idea of what we think will happen. Then we see if the data supports our alternative hypothesis, has sufficient evidence for it. Why is Mumont not doing P naught? Oh, I think it might be, you might have to type HO or, yeah, it might be that right there. Try a few different versions and he should start saying that. He should be here in the background, right? So yeah, check out, he should be here. Is he mad at us? We'll find out later. Oh, he's still here. We must not be typing the P naught correctly. So try a few different versions. It might be like a O or something. That might be it. You might say it now. With this right here, I'm sorry for me. The first thing we write when we write the null hypothesis is, or I should just write it out. No, it's better if I do this. Oh my gosh. Note. Oh, that should be it right there. Oh yeah, there it is. P naught. It's not H naught. Parameter of interest equals hypothesized value. And then the alternative hypothesis. What are the three signs for the alternative? Write them in the chat. I know, right? Doing the null. You're just doing null hypothesis and not P naught. What are the three signs for the alternative? Help me out with these three signs. I just showed them to you a moment ago. What are the three signs? Great job right there, Calvin. Amazing work. Dennis, so good to see you. Yeah. Thank you, Dennis. We're seeing some Stat1 legends right here. Dennis is the reason we have Discord, so thank you, Dennis. I'm always trying to do as much as I can on the Discord, and thank you to, we had a few people, worked on Dennis a million points. We had a few people this semester who definitely helped out way more than I helped out on the Discord. That million point also goes out to the people who were answering questions quicker than Brian. I'd look some nights and I'd be like, oh my gosh, I missed this question, but this person already answered it. So Dennis made the Discord, he made Stat Nation. Like, I'm not saying like, oh, he made it. He literally made it. Mini-term 2020, Dennis made Stat Nation. Like, literally made it. So thank you, Dennis, right there. Everyone who got help on that, it's because of Dennis right there. So legend, true legend of Stat Nation. And I hope you're doing well, Dennis. Feel free to email me or say hey anytime. Hope to hear from you, man. And so with this right here, parameter of interest has a few different things. Parameter of interest can be P, mu, or mu1 minus mu2. I always say mu2 in this channel. And so with the parameter of interest, when it's P, we are testing what? If the parameter of interest, and it's only going to be one of these, but if the parameter of interest is P, we are testing what? If the parameter of interest is P, you do mu, exactly. We're testing proportions. If it's mu, we are testing what? If it's mu, we are testing what? If it's mu, we are testing means. A mean. And if it's mu1 minus mu2, think it's two means, so it's the diff between two means. So it's the difference between two means. Now, associated with these are what we hypothesize these values to be. The null states that it's equal to the hypothesized value. So the null proportion would be P naught. And that's where we get P naught from, P naught. And then mu naught is the hypothesized mean. And then technically this one is delta naught, but usually we just assume that the difference between two means is 0. Notice how these are associated. We'll put a, well, it's too big right there. We'll put a little 1. Well, this is the first one, second one, third one, first one, second one. Just trying to tell you what's associated with what. Does this make sense with the way I've written this all down? Who understands my notation right here where I've stated we could test the true proportion to see if it's equal to some hypothesized proportion P naught. We could test the true mean to see if it's equal to some hypothesized mean mu naught. We could test the difference between two means and we could see if it's equal to 0. Now, I do want to mention this when writing nulls and alternatives. The easiest null and alternative to write is for the last chapter where I test studying and passing exam. So we have whether you studied, yes or no, and whether you passed the exam, yes or no. Tell me the null and alternative because it breaks this mold for studying and passing the exam because it breaks this mold. And this is the last chapter right here. For the last chapter, it breaks the mold I've shown you right here because we say what? Really? The last chapter breaks the mold. And so what do we say for the last chapter? How would it go? Independent, not independent. Great job, Cameron, right there. So the null is only the last chapter with chi-squared. X is independent, I can't spell the word, independent, there we go, of y. And the alternative is going to be X is not independent of y. And so you just input the variable names. Try writing it in the chat here just for practice. This is a good sheet on nulls and alternatives. Every test, or the first 2 chapters are covered up top, being chapters, I think this is 15, 16, 17, and 19 down here. Those are chapter numbers that are covered on. So how would this be written? Just try writing it out for practice. And Sarah's already done it. Nice job, Sarah. And I think Maywen's already done it. Studying and passing the exam are independent. Studying and passing the exams are not independent. Exactly. We didn't really go through the test right there, but these are the nulls and alternatives. And we always try to write the null first, because once you write the null, you'll either change it to a different sign based on the researcher's question, or you will say just not independent. Do realize that not independent also means associated right there. So really good work. I'm so happy we have so many people coming by today. That's really fun. Like we have Jesse and Moira and Dennis. Might get, if Calzone Tyrone shows up, then this is the best day ever. He was someone who showed up to our first Kahoot, random student from New York, played and placed in our first Kahoot when we did them online. So Calzone Tyrone, where you at? Come on over and hang out. Does something, the heart's blocking it, matter which variable you say first? Not really, not really. Good question, Maywin, right there. It doesn't really matter which variable you say first. Good questions, Maywin, for chi-squared. Yeah, thank you, Cameron, clarifying. Is it always a right-tailed test for that for the chi-squared? It is, Cameron, you are correct. Chi-squared is always a greater than test. You won't have to do that, but it is always a greater than test. Stellar Ferret in the lead, Rapid Dolphin, Balanced Sloth, Amusing Rabbit, and Bold Goat. Good to see you here, Bold Goat. Next question, the central limit theorem states that the distribution of the sample mean will do what as the sample size increases? Now this actually deals with the nearly normal condition. Might do this one a little bit quickly. It's kind of a review of the nearly normal. And there's 2 things that are stated about the sampling, the distribution of the sample mean. The distribution of the sample mean will do this as our sample size increases. I gotta disappear. I do have to disappear. 50 answers almost, I like it. It'll get more normal and tighter. I realized I was blocking an answer right there. This is why we can say it becomes nearly normal. This is the literal reason behind, and if you were doing the project, a few people lost points because they said Ghost Brian right there. A few people lost points because they said like, my sample size isn't large enough. Your sample size is large enough to normalize the data, and that's large enough N, which is now part of the nearly normal. So if our sample size is large enough, the distribution of the sample mean will be nearly normal. Hence, we can use things like the t-distribution. Not too much else to say on that, but central limit theorem states the distribution of the sample mean, not the original data, will become more normal and tighter as we increase the sample size. So, good stuff. Stellar Ferret, Rapid Dolphin, Balanced Sloth, Amusing Rabbit, and Friendly Yak, and how do you say that? I don't know. And good to see you again. Here we go. The confidence interval goes from 10 to 40. The margin of error would be what? I love questions like this. Hopefully you can do this one super duper quick. Now we're going to draw some stuff out here in a moment because margin of error is a really fun thing to solve. We'll talk about margin of error, and then we'll draw it out. Really excellent review, everyone. Need a haircut. Hopefully not a lot of people said green. So if you said green, what did you give? You didn't give the margin of error. What did you give for the interval? If you said green, great job, Eleanor, right there. Enchilada. It is enchilada. If you said green, you gave the full length of the interval. Don't worry if you said green. That's this. You know what that means? You know what? We're throwing out one last million points right here. I guess that's all right, because if you got everything right on this Kahoot would be worthless. It would mean I didn't challenge you. If you get things wrong, it means you're here to learn. So get things wrong. It means you're here to learn. Don't be like, oh, I'm not learning. You're learning. If you get it wrong, you're like, okay, where did I go wrong? What do I need to write down? Where can I learn this? So practice right here with me. When we do an interval, intervals have 3 parts to them. So we'll just pick one of the intervals. There's an interval formula right here, and I want you to tell me what we are trying to understand. We are trying to understand the what with this interval. What is this interval trying to understand? Go ahead and tell me. This is one interval formula. What is it trying to understand? What is that interval trying to understand? That interval is trying to understand the what? We'll mention what this notation is. Check out the videos. It's a confidence interval for the true mean. Great job right there, Lauren and Alexis. Great. You see, Lauren, I think you got this. You know what that is. That's a confidence interval for the true mean. Because if you notice here at the start, the sample mean is the best estimate of the true mean. The first part of the interval is the estimate portion. So let's write estimate above this. Then you have after the estimate, the plus or minus, which is the margin of error. So the margin of error is always a plus or minus. The margin of error in our class will have 2 components. One of the components of the margin of error is the t with a star. It also has degrees of freedom right there, which we talked about. And this is going to be your confidence level. So how confident are you is based on the t. The bigger the t, the more confident you are. Now, last part of this is called, give me the abbreviation for this, which this is abbreviated. That's standard deviation right here. We'll write S for what it is, and this is sample size. What it is. It's the standard error. So that's the standard error, which is basically an estimate of the standard deviation for the mean. It's called standard error because it comes from a sample. It's not the truth, which would be standard deviation. That's the standard error of the mean. So how in the world can we figure out margin of error if we have something like 10 to 40? Well, when you look at this interval, the center of the interval is going to be at the center. That's why, and this is the center right here. We'll also write center next to it. And the center will be at the center, not at the off center. The center's at the center, and then I would make this the yellow portion right here. Center is your best estimate of the truth. And then the margin of error is a plus or minus on the interval. The margin of error is a plus or minus. And great job with those formulas in the chat. So when you think about it theoretically, if this is the lower of the interval, the lower estimate, and the upper estimate, the margin of error is merely what the length of the interval. Like if you think about the full length of the interval, which we were given for the question, the margin of error is merely what the full length. Just think about it visually speaking. It's half the length. Thank you so much, Cameron, right there. Yeah, I want to show why it matters and what we're doing. Thank you, Cameron. That's a huge compliment. So all we're doing is figuring out how far away is the upper and the lower. And then we're taking half that distance, and that's margin of error. But what if we do the following formula? What if you take the upper plus the lower, and you were to divide it by 2? What would you find right there? If you were to take the upper and the lower and average them together. If you were to take the upper portion of interval and the lower portion of interval and average them together, what would you find then? Just think visually speaking. The center, boom. Yeah, that's it. Nice job. So the upper plus the lower divided by 2 is just averaging the values and finding the middle of the interval. So there's a lot of ways to do this. And so think about this. If we go back to our original question that started all this, what's the center of this interval? What's the center of this interval? What is the center of this interval? Look up there at top. The center of that interval is what? 25. Now state the center with the margin of error, 25 plus or minus what, which would create the interval. So then you can double check and be like, okay, this interval would be 25 plus or minus, so give the full thing and I'll pin it. 25 plus or minus what, which then that would create the interval to show you have the interval. 25, great job, Alexis, right there. 25 plus or minus 15, 25 plus 15, 40, 25 minus 15, 10. And now you've shown that you've got the interval right there. And we've also shown the math on how to get the margin of error, which would be 40 minus 10 divided by 2, which is 15. So no worries, we pinned it correctly. So good work right there. Great practice and good job reviewing. Don't worry if you get it wrong. We're here to practice. Stellar Ferret, Rapid Dolphin, Balanced Sloth, Amusing Rabbit, you got this. Loyal Lobster, still Royal Lobster, not Loyal Lobster. Next question, let's do this. Increasing the sample size will make the margin of error smaller. We actually have a perfect graphic up for this question to do it next. And feel free to hang out and watch the BAS 320 review. You'll get to see some new things like that logistic regression. And if you want, watch the 474 review and you'll get to see things like neural nets. We do a lot of fun things in statistics. What do we have right here? This is very true. Let's take a look at the graphic over here. When making a confidence interval, the margin of error has sample size in it. So take a look at this right here. Why does the margin of error get smaller if n is increased? Why does the margin of error get smaller as n increases? Why does the margin of error get smaller as n increases? Because you're dividing by it. Even if it's square rooted, you're still dividing by some aggregate of n, right? Now it gets more precise, exactly. It won't change confidence. Good answer is Maywin right there. Great job, Maywin. It's going to get more precise, i.e. tighter. Precise means tighter. That's a good note to have. Precision is how tight it is. The confidence is controlled by t. So if you increase the t, you increase the confidence. Now let me ask you this. If you go to a restaurant one time, would you have a good estimate on how much you spend on average there? If you go to a restaurant one time, your friend's like, oh, I've been to that restaurant once, you'll spend about $100. No, because your sample size is 1. If you go to a restaurant every week for like years, we're saying like 20 years, and you go there every week, so you've been going 4,000 times. That's crazy, right? You spend a lot of money there. And $100, you spend $500,000 almost at that place. So if you go to a restaurant, man, money ends up fast. If you go to a restaurant once a week for 20 years, would you have a good estimate on average how much you will spend at that restaurant? Like my wife and I used to go to, I miss going to Soccer Taco a whole bunch. We used to go to Soccer Taco about once a week. And we knew that if we went down there and we got like the Colts and shared it and got chips and then got a large margarita to share, which I drank about 2/3 of it. So it was so good. Like pitcher margarita, only if you're of age drink, once a week. I used to go there once a week and we could get a pitcher margarita, the Colts, and chips, and we would spend like, I think it was like $23, and I would leave like $30 or something like that. And like, cause like the pitcher was like 12, the Colts was like 10, whatever it was like low 20s. I would just drop a 30, give like an $8 tip. So you give a good tip, you get an amazing meal. Now prices have gone up since then, but I was pretty confident. Me picturing a not margarita. I've never had Soccer Taco. Check out Soccer Taco in the Market Square if you've never tried it. Really good place. Soccer Taco is awesome right there. Check it out. Fan of Soccer Taco, type it in the chat. Really good stuff. Check them out. Say Stats1 sent me, and they'll say, what? The Soccer Taco is really awesome. So you'd have a better estimate after going there. Live, love Soccer Taco. Check it out. Really, really good. Next question. Here we go. Our leaderboard. I think there's 3 Soccer Tacos. Actually, one near us now. So we'll go to it. Stellar Ferret, Rapid Dolphin, Balanced Sloth, Amusing Rabbit, Royal Lobster. Next question. Central limit theorem, the more data you have in your sample, the closer the shape of the sample data will become to normal. Notice I kind of squinted at this, and we'll probably go a little bit quickly through this. Central limit theorem is a little bit more on second test. It does apply to our test for the nearly normal condition. This one catches people off guards. This might actually be on the final. I'm trying to remember because we have reshaped questions a little bit. But this one is a trick question. This one is a trick question. I think I reviewed Soccer Taco. We use this a lot in forecasting. Yeah, great job, Dennis, right there mentioning it. Wait, did I get this wrong? The more data you have in your sample, the closer the shape of the histogram of that sample data will be to normal. My sad music. My sad music. This, well, we just destroyed some answer streaks. Who was in first right now? Who was in first? Who was in first? Who was in first? Who was in first? Does anyone want to say? I was Sarah. Sarah, you just won a $20 Starbucks gift card. Email me, or you could have Amazon if you want. Email me your UTK if you want, or whatever, but make sure to email me from your UTK. If a random person says, hi, this is me, and I'll say, no, I don't know who that is. But $20, Amazon or Starbucks, we're gonna give that out to first place also. So since I was gonna do that for first place anyways, you were in first right now, so you won. Since I think this is an error right here, I'm saying it's an error. 0 days since Brian got a Kahoot question wrong. So just wanna say a big thank you. Once again, we are doing this for fun. Error on my part right here. So I was just doing this to really call your attention to it. It's not the sample data that becomes more normal. It's the distribution of the what that becomes more normal. It's not your data that becomes more normal. Your data doesn't become more normal. The central limit theorem says the what will become more normal. We'll see it right here. It's not your data that becomes more normal. It's the what that becomes more normal. Yeah, just making sure you're paying attention. It's not your data that becomes more normal. It's what? So if you have data right here, here is your data, and then you do sample size of 25, it's not your data that becomes more normal, it's what? Like your data didn't change. Your sample data does not change. The shape of the what becomes more normal. There's no cash prize. I don't think I can give cash prizes. Kind of the mean of the data. But think of this, and the answer is in it. So your sample data will look like the population. So here's the sample data. This is the population of interest. Here's the sample data. The sample data represents the shape of the population. It's the what of the what that becomes more normal. So the sample data resembles the shape of the population. Population shape, shape of sample data. It's a smaller sample, so we don't see enough, but we can kind of tell it is right skewed. The what, kind of, it is the mean, but the what of the mean? And the answer is down below right here. It's not, it is kind of the mean, but it's the what of the mean, which indicates a shape of it. The what of the mean will become more normal. The distribution of the mean will become more normal. The way it's distributed, it'll be more normally distributed. That's what we mean when we say distributed. We say, like, how do you distribute these numbers across the number line? Well, the top one has a more right skewed distribution, which is the population, which is all the data. And then this one right here, it is false. So yeah, so it was false right there. That was an error on my part because the sample data doesn't become more normal. That is false. The distribution of the mean becomes more normal. And we have put this on the test. And I've had students make a 99 on the test when this is a 1-point question and say, what did I get wrong? And then we'll look and say, oh, that says the sample data becomes more normal. The central limit theorem states the distribution of the mean will become more normal, not your sample data right here. You're still on the podium. Nice job right there. Well, you could double win. You could double win. Here we go with the podium. Balanced sloth, stellar ferret, rapid dolphin, royal lobster, amusing rabbit. Next question. It's such a small thing, so hopefully remember it, but if you don't, it's all right. The t-distribution is like the normal, but it is different in what way? How is the t different? Lots of review here. Ooh, I like this. I like this. I think this is pretty easy if you know it. T is like the normal, but is different in what way? Stay to the end. We'll be doing some really big stuff. And let me put the T in the chat right here again. More area in the tails. More area in the tails. So it is not bimodal. Don't worry if you said that. But the T has more area in the tails right here. If you look, this goes out to -10 and 10. Usually we don't see that. Usually a normal curve goes out to what and what when we draw most of it. The normal curve usually goes out to what and what when we draw it. The normal curve usually goes out to what and what when we draw it. Let's leave the Kahoot. Did I still got right? I'm really afraid. It goes out to -3 and 3. And look, as we increase the degrees of freedom, you see it's go to -3 and 3 basically, and now there's no area beyond -4. So Mr. T comes in, he smashes down, says, "I'll pay the fool," and we go between -3 and 3. When it has less degrees of freedom, it's less normal, and it kind of gets this more, it looks tighter in the center, but it has been smashed down because more area entails. When do we use t-tests? When we are analyzing the what. Once again, this is a more easy question. T-tests are used to analyze the what. You know what? Let's show a t-test here because we haven't shown much jump output. We use t-test to analyze the what. We use t-test to analyze the what. T-test to analyze the mean. So if we are doing a single sample t-test, imagine this. I ask you, basic question where I'm going to try to type it. Let's say, how many sodas do you drink a week? You don't have to answer this if you don't want. Be honest though, if someone says 50, I'm not going to believe you. Don't drink 50 sodas. Maybe I've approached that sometimes, but how many sodas do you drink a week? Too many. 0. I'm down to 0 right now too. 7, 1, 0, 5, 6, 7, 10, 2, 3. Enough. 2. A few more answers here. Let's keep going. 4, 1, 0, 0. It's going to be right skew distribution if you see it. It's going to be right skew with outliers. Brian used to drink about 15, a little more than 2 a day. So bad Brian right there. So now we have 90. I don't believe you, Anna. Don't drink 90 sodas. I mean, you do mu, but mix it up. Put some water in there or something. You do mu, though. So we might have a little bit of a problem with the nearly normal condition because if we have this right skewed of data, thank you so much. Oh, yeah. Dennis, definitely. Yeah, Dennis, thank you so much. Dennis has opportunities probably working in the corporate world. So Discord's a great way with our careers channel. We're trying to get as many people to do it. So Dennis, thank you so much. In Dennis's message, he is on the Discord right there. We're always trying to get students opportunities and connect people because that's the goal, is to like give you skills and get you jobs and have you have a good life. So that's our goal right here with education. So Dennis, thank you. Thank you. We pinned your message. So with this right here, with the nearly normal condition, why are we, random news? Sure, why not? Why are we maybe probably not passing it? Because our distribution is extremely what and our sample size is only what, which is not larger than what, we probably don't pass the nearly normal condition. See if you can fill out that sentence for the nearly normal condition. Because our sample is extremely, ooh, I'll see some monster man. So because if, I don't know, jump, what are you doing? Because our data is extremely what and our sample size is only what, we don't have at least what, so I don't think we pass the nearly normal condition. Because our data is extremely what to the right, you can fill out this sentence, you're doing really well. Yeah, and you can say 100, like, or 40. Sometimes the book says 40. It kind of matters, but exactly. We have a smaller sample of only 24 people, so I don't know if we pass the nearly normal right here because the distribution of the mean probably won't be normal enough with a very right skewed distribution with only a sample size of 24. I'd prefer 40 or better yet 100. So this is maybe an issue with the nearly normal. So I don't know if we pass it, but still, let's do the t-test right here. And here's what's interesting. On this t-test, what if I told you, remember we just made up this data, right? So I can't have cheated. What if Brian told you that Brian is going to tell you the p-value and he's going to tell you the t-statistic? So this is a more advanced question here. Nice job, Sarah. Wow. So Brian's going to tell you the p-value and the t-statistic for this. The t-statistic is going to be about 2.02. The p-value is going to be about 3%. Oh man, how'd I get the t that off? Am I math wrong? Let me see my math. 5.15. Wait, what? Oh, no, I looked at the standard deviation. Whoops, whoops, whoops. Oh, why'd they have to be so close? Okay, review. Okay, we're doing that again. You ready? Okay, the t statistic is going to be about 2, and the p-value is going to be about 3%. You ready? Interpretation quest. Yeah, we'll do an interpretation right here. Rewind. Here we go. Whoopsie daisy. I looked at the standard deviation. I thought that was the mean, so that's what I was doing the mental math with. Okay, so here we go. We're going to do a t-test, and the t is going to be about 2, and the p-value is going to be about 3%. So here we go. I have to think and use it right here. So 4.625, and then let's do it. And there's the t of about 2, and the p-value is about 3%. That's the one I wanted for the greater than test. I should have told you I was doing the greater than test, but that's what I was thinking of in my head. Does anyone have any idea how I found those values? If you have any idea how I found those values, you are way ahead of the game. Like, that was not meant to be easy. This is only years of practice and knowing how to do this stuff that I was able to think through that. Let me tell you how. The mean right there is what? In notation, the mean is what? What is the mean in notation? In notation, the mean is what? Like, just tell me notation. The mean is what? Not mu, not mu. Good answer, Alexis. Not mu, though. The mean, that's from the summary statistics, though. So it's not mu. That won't be mu right there. And you might need to write this down and take notes on it. Good answer. That's why I asked these things. That's not mu, though. That's the summary statistics. So that's not mu. It's y bar. It's y bar. It's sample mean. So that is y bar. So the mean right there, good answers, is y bar. Standard deviation is S. Standard error is SE. And then this is the upper. And this is the lower. And then this is N. It does capital, or not. Is there a video where you can review the interpretations? Yes, I think so. Definitely, it would be under the speedrun reviews. I go over the interpretations there. Check those out. And also, the other reviews have interpretations at the end. Hypothesized value. A lot of people forget what the hypothesized value is. We also reviewed this, and we will interpret this right here. So, and check out our class videos too. And Hannah, if you can't find them, let me know. But our class videos, we do the interpretations. So, hypothesized value here is what? So what is a hypothesized value? A hypothesized mean is what? Not mu, is it? Hypothesized mean is what? It's mu naught, exactly. That's the hypothesized true mean. And so with this right here, this is where y bar is at. This is where mu naught is at the center of the curve. And the t statistic being 2 is very close to your 68, 95, 99.7 rule. And if 95% is on the inside, it's very close to about 2.5 if you think about doing your test right here. And it should be the less than test. I was thinking on one side of it. So the less than test would have about 2.5%. But because the t has more area, it's going to be more. Because the t has more area in the tails. Does everyone see how I kind of looped it back to the understanding? I was trying to get a t of 2, just doing it mentally in my head, and I added 2 standard errors. I backworked it by taking the standard error of 0.75 about and adding that to the mean to come up with this value right here. So I was kind of purposely testing a value that was 2 standard errors above using the theory of a t-test. And then since I know the z has 2.5 on the lower tail, I know that the t would have a little bit more, and that's why I said 3% as a guess. You're not meant to know at this level, but the t has more area in the tails, and that's why I increased the area right there. So does anyone get this, or did I go way too high level on this? If you're wondering, and just the basics here, the notation is marked right here for this. This is going to be your does not equals test. This is the greater than test, and this is the less than test right here. So someone got something out of this, if not just the notation for this, with what everything means right here, with this being the standard error right here, and this being bar. So know your notation, know what every one of these means. This would be missing this right here also. Any questions? Really high level question. We're going to bring it back to easier stuff now. Too high level. Oh, okay. Back to the Kahoot. Let's do it. Next question, here we go. Balanced law, stellar, farad. SE, isn't that standard deviation? Oh my gosh, Cameron, did I get it wrong? 2 seconds. You got to throw out a million if you're right. And my gosh, Cameron watching the chat right there and watching what I type. Cameron, you are correct. A million points might be our last points of the semester. Cameron said, Brian, that's your standard deviation right there. That is true. That is not the standard error. That is merely S for standard deviation. Great job, Cameron. Good catch. That is standard deviation, not standard error. Standard error is S over square root of n, which can be calculated right here, just to show really briefly. Since we know the standard deviation is 3.65, then we take the square root of 24. Oops, gotta cancel this. So 24 square root, and then 3.65 divided by that, and there's the standard error calculated. So know how to do things like that, like find the standard error when using output. Okay, great job, and really good practice. What is the p-value? When the p-value is below alpha, we do what? You got this. Easy one. Do not say the bad words. 2 of these answers. Well, gosh, it should be so easy. I hope. I'm scared. I'm really scared right here. Oh, good. Thank you, Ava. Ava right there has said it. Oh my gosh, what did I just do? Oh gosh, Ava. I was trying to pin your message. Ava, I'm sorry. Ava, I can cut that part of the video. I can edit that out if you want. I was trying to pin your message and I clicked right here. And if you, the message right, like if you see right here, I was going over here and Ava right there. Sorry about that, Ava. Just say subscribe to Ava. So I went right here and right, I clicked 1 bit off. If you go right there, it's go to channel if you see that right there. So sorry about that. Clicked 1 tiny bit off. I'll edit the video after this and just take that portion out. So there might be, we'll lose the chat. Oh, thank you. Okay, thank you, Ava. I was just like, oh gosh. Yeah, so sorry. I was like, what? It loaded a page. And I was like, what's going on? Oh my gosh. It's all the, luckily, I'm doing better now. So I don't care. We're going crazy on these million points. I love Ava just rolling with it right there. Ava, you're awesome. Okay, roll with it, Ava, right there. Ava influencer arc right there. I mean, if people want to drop their Instas, I mean, this is a public video on YouTube, but if people want to drop their Instas or whatever, you can always do that here. New level, Ava influencer level right there. We might have to make that at the end of it right there. So we reject the null. When the p-value is low, you reject the null. That's the first time I've ever done that, like ever. So plug yourself if you want. But remember, this is a public video. I don't have an Insta. I just do this thing. So yeah. Okay, next thing right here. Can we have your Insta? Next thing right here. Let's do it. When the p-value is low, reject the null. When the p-value is high, just let it fly. Fail to reject the null. Those are the only things we say as we have a little bit of fun. You either reject the null or you fail to reject the null. I guess I could maybe take some bunny pictures and stuff. That'd be fun. But yeah, never know. Starts to statue 1. Thank you so much, Anna. Oh my gosh. When construction and comps for the mean, which of the following do you not include in the interpretations? We'll do an interpretation right here for confidence interval, so we're about to practice that. So what do we not include in a confidence interval interpretation? Ready? Sarah's right there. A vlog. Okay. So here we go. Let's interpret the confidence interval. You ready? Write this down. We're having a lot of fun, and we're going to write this down. Here's what you'll write on the test. 8 points of the test, and my gosh, Anna has already done it, saving us time and energy. Thank you, Anna, right there. Look at this right here. I am blank % confident that the true blank is contained in the interval blank to blank. Look at this. Perfect work right there. Thank you, Anna. And Sarah and everyone else writing it for practice. Vlogmas at, I don't know, maybe we'll do stuff like that. And so right here, Now, where usually people make mistakes is this portion right here. So this is where people make mistakes. So I want you to go back to our output right here and interpret this confidence interval for the mean. So does everyone see this confidence interval right here? We can call it 1.6 to 4.6. So try to use what people have in the chat, and it's 4.6 to 1.6. You can see it in the chat. Yeah, I'd love to get a diamond play button, but yeah, long ways away from that. 4.6 to 1.6 to 4.6. Remember, we were analyzing soda consumption. We're analyzing soda consumption. So try to do this right here and write the confidence interval. So you do the I am, then you look at the confidence interval. I am blank % confident that the true something. And look at the output. I mean, it kind of tells you what it is. I am 95% confident that the true mean of sodas that students drink each week is contained in the interval. Alexis, you got it. Great job. I am 95% confident the true mean of students drinking soda, the true mean amount of soda that students drink is contained in the interval. Boom to boom. Great job, Anna, right there. I am 95% that the true population, true mean though, make sure to throw true mean in there. Make sure to throw true mean. Population average. Sarah, I'm sorry, right there. Average counts. And if the graders take out points, let me know because average is mean. I am 95% confident the true mean. Great job right there. So when will you say mean? When the y variable is what? When will you say mean? When the y variable is what? There's a check you want to do. I will say mean, true mean, when the y variable is what? Quant. You'll say proportion when the y variable is categorical. And you'll say difference when there's two means being tested. Difference between means. We'll look at some of that output here in a moment, I think. Great job, really good practice. Very proud of everybody. I think we got some interpretations for other ones coming up. There's your interpretation for doing confidence intervals right there. Okay, let's look at that leaderboard, which we didn't get to look at a second ago. Here it is: balanced sloth, stellar ferret, rapid dolphin, excited giraffe, amusing rabbit. Great job. The null hypothesis is that mu is equal to 5.2. 98% confidence interval goes from 3 to 4. You would reject the null hypothesis at the 0.02 level of significance. Let me disappear. This is a concept which is very big. So this is the value being tested. This is the interval. Nice job, pretty good work. A lot of people got it. And let's see why it is that way. I tell you a steak dinner costs between $20 and $30. Do you think it costs $50? I tell you, I've been to this restaurant a ton of times. It costs between $20 to $30. Do you think it costs $50? Do you think it costs $50? No. I said 20 to 30, right? So you would reject 50 because why? Why would you reject 50? Like this question right here. So if 50 is what you think it might cost, you would then reject that value because it's outside the interval. So when we do confidence intervals are the inside. And 3 to 4 does not contain 5.2. So any value outside of 3 to 4 can be rejected on the two-tailed test. Be very careful. On the two-tailed test, I'd fail you for your fallacies. So anything outside of a 95% confidence interval can be rejected at the 5% alpha level, and anything outside of a 98% confidence interval can be rejected at the what alpha level? Anything outside of a 98% confidence interval can be rejected at the what alpha level? Question. Anything outside of a 98% confidence interval can be rejected at the what alpha level? 0.02 alpha level. It's like an inside-outside, and then if you think inside is the confidence interval, outside is a two-tailed test with 0.02 alpha. Does that make sense right here? Like a 90% confidence interval is the analogous thing of doing a blank-tailed test at what alpha? Finish this sentence, and great job, Alexis, right there showing the math. A 90% confidence interval would be analogous and would come to the same conclusions as a blank-tailed test or the does not something test with what alpha? 90% confidence interval. A 90% confidence interval would come to the analogous conclusions, whether it contains something or not, in the fail and reject for a two-tailed test with 10% alpha. Just to draw this really briefly right here so people can see, we're saying the 90% confidence interval So the 90% confidence interval looks like this, 90%, more than 90 probably, less than. And then the two-tailed test would look like this, where alpha is equal to, and they will come to the same analogous conclusion. Because two-tailed is on the outside and 90% is on the inside. So if you make a 90% confidence interval and contains something, then you would not reject it on the two-tailed test. Does that make sense? If the 90% confidence interval contains the value, you would fail to reject it on a two-tailed test with 10% alpha because it would not fall in what we call the rejection region. Does this make sense right here? Tests and confidence intervals can be analogously used. Like doing a confidence interval basically runs a two-tailed test on 1 minus alpha level, or 1 minus confidence level of alpha. So there's your confidence level, there's your alpha level, two-tailed test because it's the outside, where confidence intervals are the inside. So key concept right there to know for the test. Thank you, Olivia, right there, and good practice. It's a really cool concept, because do you ever really need to do tests then? You could just make a bunch of whats to see what the truth is. You ever, oh man, so Sociology 119, cool. How'd you find this channel? Good to see you there. So you could actually, and this is a fun thing, you could actually just make a bunch of whats to test values, which makes life easy, because then you don't really got to run tests. You could actually just make a bunch of whats and see what the truth is. Good to see you, Sociology 119. Confidence intervals right there. You could just make a bunch of confidence intervals. Now journals and stuff probably want you to run and make p-values and do stuff like that. But if you're just seeing what the truth is, confidence intervals give you an estimate of what the truth is. Thank you. Man, I love seeing random. We'll have to check out their channel right there. So go check out, they're a real channel right there. Check out their channel. Cool stuff right there. So with this right here, we got the leaderboard. Balanced Sloth, Stellar Ferret, Rapid Dolphin, Excited Giraffe, and Amusing Rabbit. Gonna win. Next question. Which of the following are 3 things that impact beta? Directly impacted. Now be careful, there are 3 things that directly impact beta. One of these is an aggregate from beta. That's not the answer. You might have answered this. One of these is an aggregate, and it's not going to be the things that directly impact beta. I mean, of course, if this changes, beta has changed. But there are 3 things. I think I might know who Sociology 119 is. I love talking to people on campus and meeting people, so I think I met them. I think I know who they are. Whoa, look at those answers. They're all across. So you can see right here, there are 3 things that impact beta. Power is not impacted by, I mean, it is, but it doesn't impact beta. Power is an aggregate of beta. Does anyone know the formula for power? Does anyone know the formula for power? What is the formula for power? Power is 1 minus beta. So power of a test is 1 minus beta right there. And so when you do this right here, we write out 1, 2, A, B, plus minus. So a type 1 error is associated with which of the following? What is a type 1 error associated with? A type 1 error is associated with what? What quantity is a type 1 error associated with? Look at the notes. A type 1 error is associated with alpha. That is literally your type 1 error rate. Whatever your significance level is your type 1 error rate. Type 2 error is associated with beta. Now, a type 1 error can be called a false positive because it's when you reject the null and the null is true. A type 2 error is sometimes called false negative. It's because when you fail to reject the null, you get a negative result and the null is false. Now, we have to review this. Say it with me. In a type what error? Put it in the chat. In a type what error? Here's absolutely crazy. In a type what error? In a type 1 error, the null is what? In a type what error, the null is what? The null is true, and we reject it because that's a mistake. In a type 2 error, everyone see this right here? In a type 2 error, the null is, and this is an F, the null is false, and we fail to reject it. That's the 2 F's of the type 2. In a type 2 error, the null is false, and we fail to reject it. So make sure to memorize this. It'll come up in a later question with Pirate Tiny Brian here towards the end. In a type 1 error, the null is true, and we reject it. In a type 2 error, the null is false, and we fail to reject it. So make sure to know that right here. Now, going back, the three things that impact beta, the three things that impact beta, which impact power, are going to be your sample size, your effect size, and your alpha. These, if they go up, are going to make beta go down. And what is sample size? Well, it's how much data you collect. So think about this. When would you have a better idea of how sick someone is? If you collect more blood or less blood from them? When would you have a better idea of how sick someone is? If you collect more blood or less blood from them? You collect more blood. That makes sense. Larger sample, you can test more, you can run more tests, so you'd have a better idea, and you would make less type 2 errors. What is a type 2 error? A type 2 error would be failing to find that someone is sick when they're actually sick. Think of a false negative. That means if you were to make a type 2 error, you would fail to find the sick person because the null is that they're healthy, and you would fail to reject the false null, and this is not good. So if you want to really find if people are sick, you take larger samples from them and collect more data and figure out what's going on, and then you will find out they're sick if they really are sick more often, less type 2 errors. And so now we have effect size right here. Effect size is basically the idea of how sick someone is. So this is the difference between null and truth. The null being that they're healthy, and the null and truth, and the alternative being that, or the truth being that they're sick, not the alternative. So effect size is practical, right? So if you have someone like me, who I'm just a little tiny sick, if you have someone like Brian who's just like, you might not register that they're sick, but if you have someone who's passed out, that's a bigger what. Somebody who's passed out and wheeled in on a stretcher, that's a bigger what. What does that abbreviation mean? So it'd be harder to tell with Brian who's just like, versus someone who's passed out. There's a difference in what right there, which makes it easier to reject the false null, a bigger effect size. The effect size, that got serious fast right there. That escalated quite quickly. And then alpha right here, alpha is your type 1 error rate. Now, if you increase type 1 error rate, you make more false positives. The easiest way to find every sick person in the world who's sick is simply do what? Put your alpha to 1. What does that mean? The easiest way to find every sick person and not make mistakes, well, you will make mistakes, but to find every sick person for certain is to just say everybody's what? You'd make a ton of type 1 errors. But the easiest way to find every sick person is just say everybody's what? You'd find every sick person then, but you'd say everyone's sick, but then you'd make too many type 1 errors. So type 1 errors are false positives. So if you increase your false positives, you decrease your false negatives, because you can't fail to find sick people if you just say everyone's sick. Does that make sense? You can't fail to find or not find sick people if you just say everybody's sick. You just make type 1 errors then. So there's a balance. You don't want to make too many type 1 errors. Now, the best thing to change is going to be your sample size. Time and money can be a constraint on that. You can't change effect size, and we don't like to mess with alpha because that's considered bad stats to change your alpha. Now, increasing these directly increase power because power is 1 minus beta. And think about this theoretically. Why will power increase if you increase anything on the left? Like increasing anything over here increases power. Why? Like explain to me why power increases. Like with the middle ground right there, why does power increase if you increase things over there? Because it's 1 minus beta. So if they all make beta smaller, they all make power bigger because power is the complement of beta. And power is basically not making type 2 errors. So I think everything but making type 2 errors. So power is the ability to correctly reject the false null. Write that down. I'm going to repeat it again. Power is the ability to correctly reject the false null. I like to say power is the ability to find results when results exist. So beta becomes smaller, making power larger. Exactly. So by decreasing beta, you increase power. That's just the way it works. So the three things that impact power or beta are going to be sample size, effect size, and alpha right there with notes next to them. Really key lecture right there. That is chapter 16, and we're almost done. 3:20 if you're here, we'll start soon. I'll take like a 5-minute break between. Stellar ferret, balanced sloth, rapid dolphin, amusing rabbit, and excited giraffe. Next question. The hypothesized value in the null hypothesis can be any value we want it to be, true or false. Is it here on the soundboard? What did you just hear? Oh my gosh, wait, what are you hearing? I think you might be hearing a music thing. I need to hear my sound effects again. The Rock? I think it shows it's still playing. That is music, yeah. I think it's Josiah Wilkinson. Shoutouts to Josiah. Check out his channel. That's piano music, it's Josiah. I think you should hear it now. Anything is possible! Oh, well was that anything is possible? Hopefully that was anything is possible. I was looking for. With that right there, you can make the null value anything. That was anything is possible, that's what I thought. I can't hear it on my thing here. I can hear the music, but not that. Shoutouts to Josiah Wilkinson, great pianist right there. First thing we played. So with this right here, the hypothesized null can be anything you want it to be. No, it doesn't have to technically make sense, right? It can be anything. It's just math. So Bryce, really good. Bryce, we got to throw Bryce a million points. Because I guess some of them, like proportions and stuff, some of them don't logically make sense, but technically math. So that's my answer. So Bryce, that's a good technicality, because you're like, well, with proportions, we really can't go outside the bounds of 0 and 1. But mathematically, we'd still do it. It just wouldn't make sense. And it can still just math, because it's just like differences up top. So Bryce, you are right in the technical sense that some of them just wouldn't make sense to use, but can they work mathematically in a formula? Math, kind of math right there. What about proportions? Proportions should be between 0 and 1. So yeah, exactly, Olivia bringing it up right there, like, well, proportions. So, but technically math. So I do admit this is a little bit of a trick question, but simply the null value can be anything you come up with. I think that's the best way of stating it. Restrictions may apply to scope of data. Like if we get to technical, like very technical. So sorry, I don't think this is on the test, but the hypothesized value being P naught, mu naught, or difference between means. Do you think the difference between the means that we test has to be 0? My dad, funny enough, sorry dad, he mentioned this to me. He's like, wait a minute, you can test values other than 0? And I was like, yeah, it's just we usually test that there's no difference. You can. Now in 201, we've usually tested, I think one test in the history of a decade, we did something other than a no difference. That was like, students were like, what? And we're like, well, you can test something that's not a difference. Or you could just look at the confidence interval to see what it is. Your preference, exactly, whatever you want it to be. So anything is possible technically right there. Last question. I think he's going to be here.
Do I sound like Tiny Brian? Am I here? Am I here? Is this Tiny Brian's voice? Is it? I can't find me. 2 more questions. Okay, but then...
Okay, then he's not here yet, and I just found him, literally in that moment. Okay, well, that's his parrot. Oh, no. That means his parrot pulled him away over there. We'll find him. Tiny Brian parrot, you hang out with me right here. Okay. He's still alive, somewhere in the background. We'll bring him back right there. We'll bring him back. Okay, we'll find Tiny Brian. He flew away. He sailed away. Stellar ferret, balanced sloth, rapid dolphin, amusing rabbit, and excited giraffe. Next question. What is the p-value for the greater than test? Remember from our output, and we'll take a look at what this output is right here. What is the p-value for the greater than test? Should be pretty quick. It is a little tricky. Yeah, you should be pretty quick on it. Yeah. Oh, I like the parrot in the chat. I found him. We found Tiny Brian. The p-value, and very few people got it, so let's look at this. When you do p-values, let's show how to solve this, and we'll do the final question. How in the world do we get p-values? So there are 3 tests, right? Tiny Brian hype. So you guys are awesome. There are 3 tests. There is the greater than test, the less than test, and the does not equals test. So the greater than test is this. The less than test, this. How in the world, and great job, Valeria, right there. Amazing work. ETA, about 5-10 minutes. Thank you so much, Young. Good to see you here. About 5-10 minutes. So if the greater than test has a p-value of this, what is the less than test? So the greater than test has a p-value of this right here. What is the p-value for the less than test? So the greater than test has a p-value of this. The less than test has a p-value of what? And Sarah's saying it in the chat. Great job, Ava, right there, 0.88. The does not equals test, you take this right here and reflect it on the other side, and the does not equals test is what of the smaller of the two. So the does not equals test has a p-value that is what of the smaller of the two. Great job, it's 2 times. There you go, right there, it's 2 times. So you can see the relationship that the less than and the greater than are complements to each other, and the does not equals is going to be 2 times. So these are complements, means 1 minus 1 is the other, and because they're just the other side of the curve, and then the does not equals is 2 times it. So take a look at the math right here that we did on this one, and you can see if you're doing the greater than, which is the other side, here's the less than. Does everyone see the red line? It might be hard to tell, but you can see the red line, and the less than means this blue region right here is 29.02. Doubling that gets you the 58.04, which is both these regions. It doesn't show the greater than test just because it would complicate the curve too much. But above this red line, this is a red line, above this red line is the 70.98% on the curve, or 0.7098. Just do 1 minus 29.2902, and you will get the answer right there. So good work. Wait a minute, what's going on? Something's wrong with the stream here. Something happening.
I'm back. Where am I? Run. Wait. Why am I hidden? Oh no. This is impossible. Where is it? Where am I? I will exist.
Guys, I don't think Tiny Brian's going to be here. He has vanished from this world. He is broken. He is broken, and he will not return. He's broken.
Ah! I'm back. I took over Brian. Where's my parrot? Bring me my parrot. There we go. There we go. I survived the scurvy. I'm back. Tiny Brian's back. Let's do it. Tiny Brian's back. All right. Here we go. Stellar Ferret, Donald Sloth, Rapid Dolphin, Amusing Rabbit, and Royal Lobster. Here we go. No scurvy. Thank you, Alyssa. I knew I'd make it too. Last question of the day. Pirate Tiny Brian goes to the doctor. The null is that he does not have scurvy. What is a type 2 error? Review from your lecture. Tiny Parrot, you gotta go right now because you're blocking things. I'm so tiny, I'm not even blocking things. So, remember, in a type 1 error, the null is true and you reject it. In a type 2 error, the null is false and you can't reject it. You fail to reject it. You can't even see my tiny hands down here. In a type, it's small. I gave Brian scurvy is what I did. In a type 1 error, the null is true, but we're talking type 2 right here. In a type 2 error, the null is false and you fail to reject it. The null is that I do not have scurvy. Tiny Parrot, you want to come back? Oh my god. Is it gonna be? Tiny Parrot, help me out. Is it this answer? Or is it this answer? Is it this answer? What's it gonna be? Thank you, Tiny Parrot. What's it gonna be? Extra Tiny Brian. Is there an extra Tiny Brian on the screen? Nice job. He has scurvy and the doctor fails to find it. And why is that? It's because the null is false and we fail to reject it. It is false that Tiny Brian doesn't have scurvy, so he does have scurvy, but we're going to fail to find it. You want to help me out, Burb? Let's find out who the leaderboard is. I know it's no longer animated. $20 Amazon gift card to the #1 winner. Feel free to say you won in the chat. And the winner is Stellar Ferret. Amazing job right there with 18,000 points. Wow, that's a lot of points. Great job, Rapid Dolphin and Balanced Sloth. $20 for first prize and Kahoot t-shirts for everyone else. Make sure to email regular size Brian and tell him you won. We'll be starting the next test here in a moment.
What? What's going on to me? Whee! You were stellar. Nice job, Sarah. Did you win both? Wait, no. Was it Sarah? Did you win both, or who won the first part? Did Sarah seriously win both? Like, come back from both? If so, amazing work. Wow. You're welcome, Olivia, right there. Great job, everybody. Really good practice. Nice job, Sarah. That is amazing. That is really great work. Sarah, amazing work. And so, yeah, wow. Congratulations. We're going to start up the next Kahoot here in a second. I'm going to play some music. Okay, make sure to email me. We've got Kahoot t-shirts for everyone else. Now let's go over here to 320 and email them and say, hey, your Kahoot is starting up. So I'll put this here on your chat 201 Kahoot. So BAS 320 Kahoot at 4. And you can watch it if you want. Ava Influencer Level. Let's do it. Ava Influencer Level is going to be the new highest level. Thank you, Ava. Here we go. Ava Influencer Level. We need to go to the currency and go here. We have 79 people watching. I think 320's here. Say hey, 320 if you're in the chat. It's going to be 20 million is the Ava Influencer Level. We'll up this a tiny bit. Ava Influencer Level. Oh, wait, I'm editing his level. Oh, no. Okay, plus new level. Ava Influencer Level. I love it. That's going to be, I'll remember that moment. 1, 2, 3, 1, 2, 3. Okay, Ava Influencer Level now at 20 million points. The Ava Influencer Level. I think we've done it. Yep, Ava Influencer Level right there. If you made a stat so you could help students with stats that you don't go to, I know, right? I've thought about stuff like that. Best level ever, says Ava. I like it. Okay, let's grab the link to the chat. Got some people doing points, checking their points. Now, it'll take a moment. There's Brian talking in the background. It'll take a moment for it to do it. You have to be at the 20 million to get it. We should have some people there, and it'll take a moment. So I think Anna's there. So wait a moment if you want, and it'll take a moment for Mubot to register the new level, but it should show up. Mubot just has to like think for a little bit. So keep checking those levels. We'll see who first gets the Ava Influencer level. I'm so happy that people love these levels and have fun with them. I got 72 watch hours. Nice job. I think the most anyone's ever gotten this semester is near 100. So you're near there, and great job right there. I hope, you know, like I can't say anyone's grades. There it is, the Ava Influencer level by Cameron and others in the chat in that Ava Influencer level. We are doing the BAS 320 Kahoot coming up here in just a second. About to email the class. Oh my gosh. I got a 100 last. Yeah, I know that is about the toss right there. Thank you so much, Casey. I am feeling a lot better actually now. Like I've been only coughing a little bit. Go back and watch the other classes. We'll hope that this continues on, but this is the longest I've gone talking and everything. Last night I only took NyQuil one time. So thank you so much for the well wishes right there. Now at 106. Thank you, Cameron, right there. So really proud of everybody. I just played. Nope. Okay. Kahoot starting. Okay. Click here. Sending out the link. We're going to see some output and all this stuff. Sending it to 320. For not being in your class, I'm happy with my close to 12 hours. Well, thank you so much, Sarah, right there. With my close to 12 hours. Look, there's an echo on my mic. Good stuff. With that, let's head over and check out this other Kahoot. Got to bounce, Brian, but thank you. Thank you so much. Appreciate all the kind words from everybody. It really makes my day that people enjoy learning stats, because a lot of people are like, oh, I hate stats. I'm like, I understand. Stats is, you know, sometimes it's not that fun. You're welcome, Maywin. Thank you, and everyone have a great holiday season. Lots of holiday stuff going on. Log in. Let me re-log into I'm gonna go back and have a huge lunch. Logging in. See all most recent. We're about to start here in just a moment. We got the Kahoot up. There we go. I think everything's correct on this. We got here a 17 question Kahoot as output. Got the players. If you want, hang out over here. There it is. Happy holidays, everyone. You need to be a little larger. Who's going to be our first person to join here? Who's going to be the first person to join the Kahoot? We need our NES music. We got Sturdy Shark. 320, where you at? Say hey in the chat. 320, say hey in the chat. Where you at? Got Captain Possum right there. Almost every time I tell someone I'm a stats major, the immediate question is, why would you do that to yourself? Because it's data, it's understanding the world. Be like, you're getting inputs all day long, and I learn how to analyze inputs. Like, the whole world is a system of input, output. I almost said exploit. So like Shannon, good to see you. Casey, good to see you. Roshni, good to see you. Emma, good to see you. Connor, good to see you. William, good to see you. So say hey in the chat, everyone. Jaslyn, good to see you. So it's just like, I learn how to make decisions. That's what I do. I do it with math, so it's database decisions. We'll start in 2 minutes. Set a 2-minute timer.
2 minutes.
2 minutes. Arwen, good to see you. McAllister, good to see you. Rachel, good to see you. Now, the biggest thing right here I gotta say is knowing output, knowing how to interpret it. So we can't cover everything today, but good to see you. Sage, what up? Thomas, good to see you. Bryce, good to see you. Know how to interpret output, make decisions from output. That's gonna be some of your best things. Doing a lot better, not coughing, not even taking cough drops. So, I mean, I did last night, but that's it for you. Any questions right now? Royal Snail is a cookie with a bite taken out of it. I haven't seen that one yet. My fantasy league, some crazy things have to happen today for me to, my cousin has to lose, my brother has to lose. I lost like 2 games in a row, and I was like the third highest point getter one week, and I was the second highest point getter another week, and I was like, okay, 112 points. Doesn't matter when someone gets 125. And overall in the league, I think I'm 3rd on points for the whole league, and then I'm like 5th, I think. No, I'm 6th, because 2 people have to lose. I'm like 3rd on points, 6th in the league. Some close games I lost. So I got the best running back and wide receiver. Will we be able to go back and look at the VOD of the stream? Yep. You can look at the VOD anytime you want. It is live right now and it's recorded afterwards. So Jacob, good to see you here. Nayeli, good to see you. Yes. Ellie's like, you bet. We're about to Kahoot. I go for about an hour and 30 minutes. So if you're 474, and feel free to watch 474 afterwards. Elisa, good to, Elisa. Hey, Romania mod. This is a mod. Where can I find? Now I can't see the message. Where can I find the recording afterwards? Same link, same back time, same back channel. Just click the same link, and it'll bring you right back to this. So it's the same link on the same channel, and it'll have the timestamp of where the Kahoot is. Let me update that, but you know what it is. If you ever watched any of my Kahoots, I need some I'm readies in the chat. So if you're here and ready to Kahoot, I need some I'm ready. We're gonna put the timestamp here for the Kahoot. Need some I'm ready's in the chat. Jacob saying I'm ready. I am ready. I'm ready. I'm ready. Woo! See, I can actually hit the high notes now. It's the best episode I've ever hit them, which is not good. With that, here we go in 3, 2, 1. Let's go. Here we go. First question of the day is what? BAS 320 final review. Let's do it. If someone wants to predict views on YouTube, what model would they use? Uh-oh. What model? So they want to predict views on YouTube. So what model are they going to use? Very important right here. Views. How many views people get. How many views people get. We're going to review each of these concepts right here and make sure you know which one is used and when. So views on YouTube, what are you thinking here? And let's think about how we know the answer. Predicting it means it's the what variable. Predicting views means it's the what variable. Good answers, great job. So don't worry if you got it wrong. Predicting it means it's the what variable. If this is what we are predicting, it means it's the what variable, not the predictors or the explanatories. It's the why variable. If we want to predict this is what we want to predict, what we want to understand. We want to predict your views, that's going to be the why variable. And so that means we're really picking between logistic and linear. What is the difference between logistic and linear? There's a keynote, write down these notes. Logistic has a what variable for the y, and linear has a what variable for the y. Logistic has a what variable for the y, and linear has a what variable for the y. What is the difference between logistic and linear? Logistic, and right there, Arwen said it, categorical is logistic, linear is quantitative, but be careful. And Emma, good answers right there. Emma, good answers. The x's are a tiny bit different. The x's can be quantitative or categorical in both linear and logistic. And usually we use quantitative x's, that's what you usually see. But if the x is categorical, it will create what's is. Oh, Adam Richmond, good to see you right there. Awesome, doing well. If the x's are categorical, they will create what's. Like if we use handedness, right, left, ambidextrous, is another note to have. If x's are categorical, they will create what's. And they can be used in linear or logistic. It's just your x's. Your x's, if they're categorical, will create what's. Close. Not levels of interest. That's for the y variable. We can deal with model hierarchy. So think about this. Here's you ready. This is a good review. 7 days of the week, there will be 6 what? 7 days of the week, there will be 6 what's. 7 days of the week, there'll be 6 what's. There'll be 6 what'ses. Indicator variables. And there'll be 1 what. There we go, good answers. There'll be 6 indicator variables for everything but Friday. And there'll be 1 reference level. So indicator variables and reference levels are for what'ses. So write this down if you don't have it. Indicator variables and reference levels are for what'ses. Indicator variables and reference levels are for what'ses. Indicator variables and reference levels are for what'ses. So be able to finish that sentence. Indicator variables and reference levels, because first alphabetical. Good question, Jake, right there. First alphabetical. The first alphabetical is the reference level. Indicator variables are for what'ses. What kind of variable and what type? Is it a y? Is it an x? Is it a categorical x, as Nayeli said? Exactly, categorical x's. Indicator variables and reference levels are for categorical x's. Level of interest is for a what variable. Level of interest is for a what variable. The level of interest is for a what variable. When we talk about the level of interest. Don't worry about getting these wrong, this is just practice. Categorical y. And if we are doing a categorical y and we have a level of interest, we are doing what regression. If we're doing a categorical y and we have levels of interest, we are doing what regression. If we're doing categorical y variables, we are doing logistic regression. Good job, Michaela, right there. We're doing logistic, and linear regression is when y is quantitative. Does this all make a little more sense right here? Everything on the screen and knowing what to use and when and what these terms mean is very important to understand. Indicator variables are for categorical x's. If we have seasons of the year, there will be k-1 indicators. So there'll be 3 indicators and there'll be 1 reference. And the reference season of the year would be what? Because it comes first. What is the reference season of the year? Because it comes first. The reference season of the year would be what for the categorical x's for season in a model where there's season of the year. It'd be, but season, not month. That is the month. Season would be fall, correct? Because fall comes first. Months would have 12 levels, 11 indicators, reference level, April right there. No worries, this is good practice. In the lead right now, diplomatic chicken right there, excited leopard, friendly bunny. Oh, you know who I'm voting for. And eager glider and wise griffin. Let's check out who's going to win with the next question. What is the typical miss the model makes? Quick note to have, and we should have this memorized. This is a lot of output to look on the screen, but your eyes should immediately go to the typical miss. We are predicting GPA of individuals right here from their weight. Weight is actually statistically significant. This is a simple regression because it has 1x in the model. Lots going on, but what is the typical miss the model makes? When you hear typical miss, what 4 letters go into your head? When you hear typical miss, what 4 letters go into your head? When you hear typical miss, what 4 letters go into your head? RMSE, which is also known as residual standard error. So we want to find the RMSE right here, and that is the typical miss the model makes. The other one people put down was the very small 0.00006. That is the standard error, which is your uncertainty in the estimate of weight. Does that make sense? I think weight has a coefficient of this, but I could be off by about this. This value right here represents how much you are unsure of in your estimate. As in, I think a steak dinner might cost $30 at my favorite restaurant, but I could be off by 5. Now, how would we construct a 95% confidence interval for the price of the steak? Really quick bonus question on this. If I think a steak dinner costs $30, but I could be off by 5, how would you construct a 95% confidence interval very quickly for that? So if I think a steak dinner could cost $30, we're just putting 30 as the estimate of whatever we're trying to do, and then the standard error, which is our amount of uncertainty, is 5. How would we make a 95% confidence interval for it? It goes back to Stat 201 with the 68, 95, 99.7. So how would you take 30 as an estimate with an uncertainty value of 5, which is what this quantity represents, is the amount of uncertainty, and then use a 95% confidence interval? Think about how you would do the 68, 95, 99.7. What would the 95% confidence interval be? Right, great job, Jacob. Go ahead and solve it, though. So you'd say, I am 95% confident the true price of the steak dinner at the restaurant is going to be contained in the interval blank to blank. So go ahead and do it right there. Jacob's got the formula right there showing how to do it. Because the 95%, which is basically 2 standard deviations, Jacob put 20 to 40, this is going to be used to make confidence intervals right here. So think if the standard error gets wider, this is a big review right here, if the standard error gets wider, what happens to your confidence intervals? If the standard error, which is your uncertainty in the estimates of coefficients, if the standard error gets wider, your confidence intervals will get wider. If the standard error gets wider, and look at the formula Jacob wrote right there, plus or minus 2 standard errors. So if the standard error gets wider, your confidence intervals will get what? If I say the steak dinner costs $30, but I could be off by 30, the confidence interval will do what? If the standard error, which is how uncertain you are, gets bigger, then your confidence intervals get bigger. And if your confidence intervals get larger, then what does that mean? They could increase, well, we're not technically increasing the confidence though. This is just the metric of uncertainty we have. So standard error is not technically level of confidence, it's just metric of uncertainty. We'll make Casey a mod too, which every name I recognize 100% will be like. So with this right here, we don't want our confidence intervals to be wide, because if our confidence intervals get too wide, what unique value might they contain for an estimate of the truth for a coefficient? That would mean it has no importance. If you make really wide confidence intervals, your confidence interval might contain what unique value, which then means, I guess it's not important, or maybe it's not, and then our p-value would be above 0.05. If you get too wide of confidence intervals, your confidence interval could contain 0. Great job, Niall right there. It could contain 0. And 0 is where you think it has no impact on the model because you estimate that the true coefficient could be 0, which means you estimate it might have no impact, which means it's not statistically significant. And so lots going on in this output. This is a simple regression, but the typical miss the model makes is the root mean squared error. Degrees of freedom we don't want so much use in this class, but please, please, please ask questions if you have it. You're going to see a lot of output, do a lot of interpretation right here, which is important for the test. Next question right here. Let's continue on. Or leaderboard: diplomatic chicken, excited leopard, honest lobster, wise griffin, and friendly bunny. Here we go. Hop back into the lead, friendly bunny. What is the misclassification rate of the model? Ooh, I love these types of questions. Nice and easy. Let's zoom in a little bit here so you can see it. Misclassification rate. I'll zoom back out in a moment so you can see the answers. You're going to do some quick math. You're going to have to know which numbers to use and how. Here's a hint. There's only 2 viable answers, and you don't lose points for guessing. You don't lose points for guessing. There's only 2 viable answers. You don't lose points for guessing. Pretty good job right there. Pretty good job. Now I know the text was a tiny bit small, hence why I was zooming in. Let's talk about this matrix right here. There is what is called the on diagonal. I'm actually going to screenshot it. What is a number on the on diagonal? You've heard me mention what is called the on diagonal. What is a number currently on the on diagonal in this matrix? What is a number currently on the on diagonal in this matrix? Just a number on it. The on diagonal. The on diagonal means this right here. Well, that's going to be one of the numbers we're interested in. I'm not doing the full sub yet. The on diagonal is when things match up. Does that make sense? Like, this is when something is accurately predicted. Don't worry, Niall, you're going for the real answer right here, which we'll go to in a second. That means something was predicted no, and it was actually no. This means something was predicted yes, and it was actually yes. Does that make sense? So this gets you your what rate. If you add up these numbers here, and you get the things that are properly classified, this gets you your what? Your accuracy. Great job, Niall, right there. That gets you your accuracy. So go ahead and compute that if you want right here. It'd be 11,094 plus 89 divided by 13,594. Notice that's the majority of the data. Now what you can do is if you get this accuracy, and if anyone wants to type in the chat, please do. Remember, this is your time to practice. Make sure you're running these. The more you practice these, the easier it gets to be like, oh, well, accuracy is the on diagonal. It's when the no's and the yeses match up with what they were predicted and actually are. And then we have the total we're dividing by. So it'd be yes, yes, plus no, no, divided by grand total. And with this, how can you get misclassification? So the misclassification is easy to find. So the misclassification is simply, great job, Nieli. So we can see from that, if that's 82%, the misclassification is going to be about 18%. Now you can get the misclassification by doing the off diagonal. The off diagonal would be these, and you could add those up and divide by the grand total and get the misclassification rate. So it'd be 2,310 plus 101 divided by 13,594. Does that make sense? And you should get about 18% or 17.74, right? 0.1774. But do remember that misclassification and accuracy are complements of each other. Any questions on this? I think I have one of these coming up. Does anyone know the accuracy of the naive model? Who knows the accuracy of the naive model? Nice job, Arwen. Boom, answer right there. Arwen got it right. The naive model uses what is called the majority level of y. And you only use the actuals. So you go over here, and you take the majority level, and there you go right there. That is the naive model's accuracy. And we'll do a little color coding on this, and I'll disappear so you can take screenshots or try to write it down too. It's a good way to do it. The accuracy is going to be that. The misclassification rate is going to be this. They are complements. And little screenshot color coding right there. You would use, I guess, used in both of them. It's used in all the formulas right there, the total. Any questions on this, like what the naive model is, what the accuracy is, what the misclassification rate is, and when would we use the confusion matrix? When the y variable is what? When would we use a confusion matrix? Great job, Arwen. Yep. When the y variable is what? Because we're predicting if something is yes or no, so this sounds like a topic from what chapter? When the y variable is what? When would we use a confusion matrix? Any ideas? Categorically, exactly. Next question. Thank you so much. Yep, y variable is categorical. Logistic, great job, Shannon, right there. Make Shannon a mod too. The naive is chosen since predicted no is bigger. So nice job, Emma. Oh my gosh, great answers. Yes, it's the majority level. Great job. Emma, great answer right there. Emma said, and I'll show it once again, then we'll do the next question. Emma said, the naive is chosen since predicted no is bigger. Exactly, it's the majority level. So we choose actual no. No, not predicted no. Sorry, Emma, thank you for clarifying this. When you do the naive, you only look at the actuals. Does that make sense? Don't look at any of the predictions because those come from the X's, and the naive does not know the X's. So when doing the naive model, the majority level is what most things actually are. Does that make sense? So the way you know which one we're going to use to do the majority level is only from the actuals, because the predictions come from the x's. The naive model only looks at the y variable, so it doesn't even care about the x's. So as Rock would say, so good questions, Emma, and thank you for that clarification. Really good point of clarification to make sure people know what's going on right there. So the naive model doesn't use any of that stuff right there. It only uses the actual values of the y. Good question. Shining quail, wise griffin, friendly bunny, blue hen, and diplomatic chicken. Next question. What does this output indicate? Oh my gosh, what output are we going to see on the screen? Here we go. There's the output. You should see very quickly what it is and know what it is. Very easy to see what's going on right there, if you know what it means. Show it again. Remember, take a guess if you don't know. Nice job. What is the point of a check regression? Just repeat after me. The point of a check regression is to do what? What is the point of a check regression? What is the point of a check regression? Just use the words of it. What are regression? What is the point of a check regression? To check the regression to see if we should be doing it. So to determine if it's appropriate, right? Is this a good idea? Should we do this? I'm checking to make sure I should be doing this. So when you do logistic regression, we have two checks in here, and I like to equate it to two friends. So the null hypothesis could be stated that the logistic model is appropriate to use. The p-values here are what? That's what one should know. P-values are what for these? The p-values for both of these are very, very what? The p-value for both of these are very what? Very high. So let the null fly. So that means we do not have evidence that the model's not appropriate. So we would continue to believe the null that the model is appropriate. In short terms, we should use this model. This says nothing to how good the variables are. It's like me asking you, do you think it is appropriate for me, let's say, I ask you, I've got this really cool puffy jacket, and I've got like really heavy pants, and then I've got ski boots. Best drawings ever here. And today it's going to be 105 out. Do you think that model is appropriate for the temperature outside? Do you think, with it being 105 degrees out, this heavy jacket, heavy pants? No. So you'd reject that model. You'd say that's not appropriate for this. So when we have data, and the data follows a form like this, and we're saying people liking a cake, we bake a cake at certain temperatures, and we ask people if they like it. The cake reaches certain internal temperatures. And we might have a weird peak down here. I like cake better. And so here the cake reaches internal temperature 300, 500, 100. Is it appropriate to fit the sigmoidal curve to this data of where people like or don't like it? Green means they like it. Black means they don't like it. Is it appropriate to fit the sigmoidal curve to this data? Two haters in there. Is it appropriate to fit the sigmoidal curve to this data? Why or not? The sigmoidal curve would fit in S shape to this data, but this data does not follow an S-shaped form. So we'd have to fit something that probably looked like this to this data, and it doesn't fit that data well. It might even fit a flat line because that's the least SES. Like if you have a S and it becomes less SE, it goes through a flat line as it goes from sigmoidal positive to sigmoidal negative. So the least significant S shape, and maybe we'll get like a thing like that because that peak at the start, but does everyone understand fitting the sigmoidal curve is not appropriate to this data? So running a check regression would come back with a what here? What would the p-value be on this check regression, which would indicate to us the sigmoidal curve is not appropriate to fit to this data? So what would the check regression p-value be on a check regression of seeing it? It'd be low. So it'd be something like p-value equals to this right here, indicating to us exactly, indicating that the fit of a sigmoidal curve to this data, you only fit the sigmoidal curve when the p-value, no. So this is what's interesting. So the null is that it's a good fit. So if we had data that was a good fit, and this is only check regression p-values, this is not p-values of variables and models. The check regression p-value tells you if you should be fitting it. Now look at this data and tell me why fitting the sigmoidal curve, and use a M word, why fitting the sigmoidal curve is probably a good idea right here. Why is fitting the sigmoidal curve probably a good idea for this? Because this data is very what? Multisyllabic word. Monotonic. Great job, Naeli, right there. It's monotonic. It goes in one direction, and it fits an S shape to the data. So this bottom one would have a p-value something like this, telling us we do not reject the null, that the logistic model is appropriate. It has an S shape, a sigmoidal S shape. So that the logistic curve is appropriate to use in the bottom. The logistic curve is not appropriate. The true shape of this data right here is this, where the true shape of this data is pretty much an S shape. Maybe we're just a tiny bit off the true shape, but it's close enough that we think it's appropriate, as in the data we see resembles what we would expect to see given a sigmoidal shape if we go more classic statistic. So classic statistics would say, I fail to reject the null hypothesis that there is a sigmoidal shape right here. The data I observed is likely to occur given there is a true sigmoidal shape. Classical statistics would say, I reject that the sigmoidal shape is a good idea right here. The data I observed has an unlikely shape or unlikely form given the sigmoidal shape. Given the truth is a sigmoidal shape. Does that make sense? Hopefully a little more in depth on what these tests are telling us. And this is only check regression p-values. This is not all p-values right here. The conclusion of this result is that we should not use the sigmoidal here. And the conclusion of this test is we can use the sigmoidal down here due to the high p-value. This is only p-values on check regression for logistic sigmoidal curve. That's not all p-values. P-values are statistical significance. But what is the conclusion? We can use the curve. That's the important part. Okay, Shining Quail in the lead right there. Friendly Bunny, Diplomatic Chicken, Blue Hen, and Honest Lobster. Next question. How many assumptions do we fail? Watch out for the trick. This is a little tricky right here. I know someone's going to lose points right here. Be very careful. Now, how many assumptions are there? And let's talk about assumptions right here. Someone's they're gonna say, wait, and I'll say, but technically. I'm sorry if you put an extra one here. That's a hint. There's a duplicate test. That's the hint. There's a duplicate test. So I'll explain why the answer is the way it is, but first off, when do we fail assumptions? This is a number one note to have about check regressions and assumptions. This is the linear check regression for a simple regression. Multiple just shows multiple p-values on the x's. When do we fail assumptions? When p-values are what? Note to have. When doing a check regression, well, if the sample size is less than 25, we can't use these. We can't look at the plots for a second check. When the p-value is below 0.05, that is a failure of the check regression. That's only check regression p-values, because the null is that linearity is good, the null is that equal spread is good, and the null is that normality is good. Is the overall model the same? That's the trick to this. And that's a little bit, I don't think the test will trick you like that. But the overall model and weight are the same because there's only one x. So that's actually just one test on the x. Because in the simple world, the overall model is your x variable that is going to be explanatory. Now, the three conditions for linear models are equal spread around the y variable, homoscedasticity, normality of residuals, and the linearity of the x, or x's for multiple models, and then the overall model for the multiple world has linearity. So clearly, we fail what test right here. Type in the chat that we fail the what, and we fail the what. We clearly fail these conditions. Which conditions do we fail? This is a good check. Make sure you can write these things to be like, oh, we fail this condition, because the p-values are here. which means there's problems. We would be worried about this and worried about this. Should we use the regression? We might. Like is it appropriate? We failed the linearity of our x and the normality. So is regression appropriate here? There's issues. Maybe we shouldn't. Sample size is at least 25, so we can go and look at the plots for a second check to see how bad we failed them. Great job right there. Okay, next question. And the overall model is the x. That's why it's technically 2. So let's watch out for the trick right there. What we fail the p-value for we fail linearity. We think there's some other model than the linear model, and we failed normality of residuals. We think the residuals do not follow a normal pattern. We have evidence against them following the normal. Good questions, Natalie, right there. Next question or leaderboard: Shining Quail, Friendly Bunny, Diplomatic Chicken, Honest Lobster, and Blue Hen. Next question. If we fail the test with the p-values, we can't use the regression model. So you fail those tests, you can't use the regression model. You're done. If you fail the test, you're done. Is that the way it works? This is recorded, can be viewed anytime later. If you fail the test, are you done? Is it game over? No more. What do you do if you fail the tests? You're not done. That is false. Nice job, Young, right there. What can you do if you fail the test? What is your saving grace? Well, these tests can be overly sensitive to large sample sizes. That's why we have a second check. You can continue on if your what is what, and then you get a second get a second saving grace. If your what is right above my head, you get a second chance to use these as long as your sample size is what. So you would then go look at the plots as long as your sample size is greater than 25. So if your sample size is greater than 25, you can look at the plots and see how bad the conditions are. So the plots let us see how bad we've done. The plots are our second saving grace, or our only saving grace, to maybe use it to say, well, even though we failed, large sample sizes can lead to high power, which means we reject the null and all models are wrong. So our model's probably wrong. So we probably have issues, but how bad are those issues? It's like saying, I think there's a problem with this car, and then we diagnose it. Does that make sense? I think there's a problem with linearity. I think there's a problem with normality. Now I'm going to look at how bad those problems are because our sample size is large, and we might have a problem that's kind of not that big, but the tests are finding it. Any questions about this? We'll probably look at some diagnostic plots here in a moment. I've got a lot of different output in these slides, but can we check the plots even if all, yeah, exactly. Great job, Emma, right there. Yes, if you fail the tests, you can look at the plots as long as you have a sample size of 25. Do you technically have to? That's our guideline. So we'd like to have a sample size that's slightly large. And here's the truth. If you only have a sample size of 10 and you fail these, your plots will look really bad. So what's wrong with the first two p-values? They're below 0.05. Below 0.05 means you fail a condition in a check regression. The only one that is passed is the equal spread because it's above 0.05. Remember how the p-values in check regressions work? Low p-values means you reject the null, and the null is that you meet the conditions for all of these. Now, go. Let's do the next one. Our leaderboard: Friendly Bunny in the lead, Shining Quail, Diplomat Chicken, Honest Lobster, and Gold Egret. Next question. So if we fail the test and our sample size is greater than 25, we can use the graph. Then you can look at the plots to give yourself a check. Good answers, Matthew. If you fail all the tests, then you're going to have to look at all the plots to see if you pass the conditions, like doing a visual inspection. Which assumption can be checked with a QQ plot? So here are the plots. The QQ plot, which is quantile plot, also known as a normal probability plot, is the one on the far right. It's also known as a QQ plot for this, and that'll tell you which condition you're checking. So the plot on the far right checks what condition? The plot on the far right checks what condition? Good work. And we only had a few people type linearity. This is not the linear model right here. Don't worry if you did that, but that's not the line. This is a perfectly fit what curve to see if our data follows it. This line down the center is a perfectly fit what curve. to see if our data follows it, which there's huge problems at the end. And you can also see it down here, and you notice this is red and that's red right there. So this is a perfectly fit, a one-to-one matchup of what we'd expect if it's this versus what we observe, the normal. That red line is a perfect normal, and these bands are kind of your it's not so bad lines. But down here, look at this, and that's why we have these low outliers down here on the histogram. Don't generally look at the histogram because binwidths are deceptive. The QQ plot for normality checks to see, I'm there, good. The QQ plot for normality checks to see if it's normal. What is the point of this plot over here? You do see the outliers down here, which are over here, but the point of this plot is to look at the line, the linearity of the data, which is not that bad. This is the same output we have. Your number one concern for this model would be its what? And you can look at equal spread. Great job, Nayeli. Equal spread can be done on that far left plot too. Your number one concern on this model, would it be the linearity, the line cutting through the middle of this? Would it be the equal spread, the points are equally spread away? Or would it be the normality of residuals? What would be your number one concern with this data? Your number one concern with this data would be what? Number one concern. Number one. The worst, most pressing concern I would say is what? The normality of the residuals probably heavily influenced by large outliers. Here's the large cluster of outliers. Outliers and normality of residuals, boom, R1, great answer right there. And everyone, there's a little bit of skew on the right side or a little bit of weirdness, but I would say it's the normality of the residuals, the cluster of the low ones. That is my number one concern with that data right there. So good work. Continuing on, leaderboard, Friendly Bunny, Diplomat Chicken, Golden Egret, Honest Lobster, and Wise Griffin. Good to see you here. Next question. Let's do it. Which level has the strongest relationship? Oh. So the no, I wish I weighed less is the black line. The no, I wish I weighed more is the red line. The yes is the green line. Which of these has the strongest relationship? Strongest simply means what is what. In the linear model, which everyone got, strongest simply means steepest what. So everyone pretty much got this. We'll do some more difficult things with this too. Steeper slope, right? Now here's the thing. How many variables are in this model, x's and y total? How many variables are in this model, x's and y total? So how is the final setup again? Half of it is recently. It's so we won't do stuff from the very start. At least I'll double check with Petrie. But it's cumulative, and so now you're seeing a multiple linear regression. So you're seeing things like dealing all with regression. So it's everything through model building. So it's the last half of the course, but it's cumulative in knowledge building. That's the issue right there. Young, good question right there. How many x's are in this model, or how many variables are in this model? That's so good question. I'll make Young a moderator too. How many variables are in this model? Final will be like the midterm where it's on Canvas, and it'll be the concepts covered since the midterm, but they do build is the issue. How many variables are in this model? Does anyone know? Don't worry, take a guess. You might want to say a full sentence, then a number. But how many variables are in this model? We have an answer 4. There are, okay, wait, Michaela, you might be right. Michaela might be, if you might need to go into greater detail. Can anyone give me a more detailed answer and then I'll explain why? How will the bonus come in play for our class points? I had it at the very end, so the class points, I'll do up to the 1.3 I usually do. I max push anyone to the next grade level, so I look at where people are at in the class, and then I assign that based on, if you have like the top, you get the biggest increase, and I usually come up with some scales, so it's class dependent. You are kind of competing a little bit, but I'm very generous on how I give it out, and I edit it all in. I did that like a few days ago. So I'm going to be very specific. 4, because technically the x value, also a variable. So let me explain. So there's a lot of ways to answer this, and I'm going to be as specific as possible. Let's grab this and show what's going on with this data and know exactly what we got right here. Okay, so looking at this right here, This is one x variable. This is another x variable, and this is a y. That's x. So you could say there's 3 variables. But here's the thing. The x variable satisfied with weight has how many levels to it? The x variable satisfied with weight has how many levels to it? The x variable satisfied with weight has how many levels to it? Be careful. Satisfied with weight has how many levels to it? The x variable satisfied with weight. But it's not yes, no, though. Good answers. It has 3 levels to it. So it has 3 levels. Does that make sense? It has 3 levels. If you have a 3-level categorical variables, how many of them are the indicator? Ooh, wow. Sorry. Now I'm good. If you have a 3-level categorical X, someone could say something really big because I just saw it too. If you have a 3-level categorical X, how many of them are indicators? If you have a 3-level categorical X, how many indicators? 3-level categorical X, how many indicators? 2 are indicators. How do you know visually? How do you know visually which one is the reference? How do you know visually which one is the reference? It'll be first alphabetical, but how do you know visually which one is the reference? It might be hard to see. The black line, that's always the way it is with our output. I can't promise every program will do it the same, but with R, the way we've coded it, it will be the black line. You could recode it, but that's just the way it does by default. It'll be the first alphabetical. So here's what's interesting. There's more variables. And why are there more variables in this? Take a look inside of here and explain to me why I have yet to list out all the variables. Because there is the y variable, height. There is weight. There is weight. There is no more. No, I wish I weighed more. And there is yes, but there's more. There's 2 more variables in this model. And you have to look inside of here to see it. What is different about those lines? Not just the intercepts. Great job, Emma, and Nayeli too. Great job, the interactions. So that means you have the variable no more, no, I wish I'd weighed more times weight. And you have the variable yes times weight. How do you know there are 6 variables in, did someone say 6 to start? How do you know there are interactions in this indicator model? Because the whats are different. What tells you there's interactions here between a quantitative X and a categorical X? Because the whats are different. Indicates an interaction. The slopes are different, and they cross somewhat, right? The more they cross, the stronger the relationships, the more they're parallel, the weaker the interaction. And so the slopes are different, indicating to us there is an interaction right here between the variables. So really good stuff. Are we doing logistic or are we doing linear here? Are we doing logistic or linear? Are we doing logistic or linear? What are we doing, logistic or linear? When I ask that question, you should look right over here. Answer the question. Are we doing logistic or linear? Not logistic, though. Not logistic. Don't worry. Why is it still linear? Why is it linear? Don't worry if you get it wrong. I ask these questions because you got to ask a lot. Quant Y. Don't worry if you got it wrong. Good practice. Height is numeric. Height is quantitative. And technically, we're kind of doing QQ. We're throwing in some indicator variables. Linear with categorical X's. Indicators. Great job, Thomas, right there. Linear regression with categorical X's. So that creates the indicator variables. Indicator variables up there at the top. And we are doing interactions with them. So this is kind of where we've gotten to, where we have linear regression with interactions on a categorical X right here. Knowing the key terminology and when it's used is important. So good stuff. Friendly Bunny, Diplomat Chicken, Golden Egret, Wise Griffin, and Dynamic Bobcat. Let's see who's got the next question. Multicollinearity is what? What is multicollinearity? Oh, I love this. This is GG pairs. Really nice graphic to do a correlation matrix right there, showing you with the groups even. Man, you can do so many cool things with GG pairs. So what is multicollinearity and how is it measured? Does anyone want to put the 3-letter acronym for the metric of multicollinearity that we get? So there are 2 possible answers right here, and great job people who picked them. Multicollinearity does not invalidate a model. It is shared variation in your x's. You have only one y at this point, so there is yeah, there's a way to do it. We don't do it. So, but shared variation in the x's. What does that mean? Your x's are whatting your x's if they share variation. Your x's could be used to what your x's, which is not a good thing, which is actually the value r squared sub I, which is the amount of shared variation. So your x's are whatting your x's. Your x's are explaining your x's. That means they're bringing the same sources of information to explain y, which is not good. You want your x's to bring what information or do what things in your model to be statistically significant. To be statistically significant in the multiple world, and I bet teacher's writing a question that sounds like this. Lisa said it right there. You want them to bring new or unique information that is not redundant. What is the metric? And write these notes down as we say them. What is the metric by which we examine redundancy in the x's to get a value of multicollinearity to know how redundant this x is with the other x's? This is not a good value. So what is the value to examine the redundancy? What is the value to examine the redundancy? What is the value to examine the redundancy? Not quite r squared. Good answer, Emma. It's a 3-letter acronym, VIF, variance inflation factor. And variance inflation means how much has the variance is standard error, so how much has our uncertainty been inflated, variance is standard error squared. For that. And McAllister, great job, I was literally writing that out. And technically of I. So variance inflation is also standard error squared inflation factor. With that in mind, remember standard error is in uncertainty. So is inflating your uncertainty a good or bad thing? So if we're saying uncertainty squared inflated factor, is that a good or bad thing? Is uncertainty squared inflation factor, because variance is standard error squared. So is uncertainty squared inflation factor a good or bad thing? Increasing or inflating your uncertainty, is that good or bad? Just think of it like I'm going to increase or inflate my it's bad. That means you are saying my uncertainty is growing because of this. I have more uncertainty. So VIF, variance inflation factor, is a bad thing. It doesn't invalidate the model. It would make us more uncertain. Because think about this. If your x's bring the same sources of information, you'd be what about which x's to put more in the model? If your x's are bringing the same sources of information, high variance inflation, you'd be more what about which x's to put in the model? You'd be more what about which x's to put in the model? You use the words we were just saying, because you'd be like, oh, good. Because they're doing the same thing, so I don't know. You'd be more uncertain, more unsure, and this is what you're inflating when they bring the same things, because your model doesn't know. It doesn't care which x's you're using.
It doesn't matter.
It's going to be uncertain, say, well, they're doing the same thing, so I don't know which ones to use. With that in mind, variance inflation factor is measured by the formula 1 over 1 minus r squared sub I. We can do 1 over 1 minus r squared of the model to get a metric based on the model of how high it should be. But let's say the variance inflation factor we get is 16. If the variance inflation factor we get is 16, about how high or about how many times has our standard error been increased? 16 is a nice number I picked for a reason. Remember, variance inflation factor is standard error squared inflation factor. So if, we got it right there, because it's just square rooting it. So you just square root it, and that's what you get. So throw in a calculator if I give you a weird number, but 16 is a perfect square, so it's about 4 times extra. So you know what that means? Your confidence interval is going to be what? Because remember, standard errors make confidence interval. If you think of the formula that So think about what happens when you inflate your standard error by 4 times. Just theoretically on the formula we wrote, plus or minus 2 times standard error. So if your standard error is 4 times bigger due to uncertainty, your confidence interval just got what? Your confidence interval just got what due to multicollinearity? You just increased your standard. It's got much larger, 4 times larger, right? And if it gets 4 times larger, it could probably include what at that point? I mean, it might or might not. But if it got 4 times larger, it could definitely at some point start to include what value? If it got 4 times larger, not outliers so much, 0, because that's an estimate right there. Good answers right there. It could include 0. And at that point, you would think that this x is no longer what? Because you'd say, well, this x could have an impact of 0. So I no longer think that this x is a what variable in my model due to probably variance inflation, high amount of overlap with the other x's and uncertainty of putting in the model. So now you would think it is what? Because if you estimate it might have an impact of 0, that sounds like what? If I say this x is worth nothing, you would say that that x is not what for the model? Not statistically significant. Not statistically significant. Good job. A lot to talk about there on multicollinearity. Doesn't invalidate the model, but I don't know. Take a look at it. Any questions, please ask. We'll look at the leaderboard. Diplomat Chicken, Friendly Bunny, Wise Griffin, Golden Egret, and Honest Lobster. Next question. What do the variance inflation factors indicate? Oh, so we should get this. It's a review question now. Oh my gosh. Does anyone know what the best VIF is? Take a look at the formula, and I want you to think about what the best VIF is. Great job, William. William said it. William got it. If your variance inflation is 1, that means that your variance was what? Because this is a factor. If I inflate your salary by a factor of 1, what happens to your salary? If I inflate your salary by a factor of 1, what happens to your salary? Is there a way to get rid of squiggly lines in R? Mikhail, you might have to email me or send me a message on that. It doesn't change, right? So we would get a variance inflation factor of 1 when the x's have what? So look at the formula again and think about when we would get a variance inflation factor of 1 when the x's have what? Good job, Arwen. See you later. Check out later if you want the rest of you. We'd get a variance inflation factor of 1 when the x is what? We'd have a variance inflation factor of 1 when the x is what? A variance inflation factor of 1 can only be achieved when what? No multicollinearity, no overlap at all. They're completely independent. They can bring completely non-redundant new information. Michaela, great work right there. And so what would r squared sub I be? So think theoretically, if they don't share any variation, the r squared sub i's would be what? So look at the formula again right here and think, if they don't have any shared variation, and r squared sub I is the amount of information in the ith x contained in the other x's. So it's how much of the ith x is explained by the other x's. If they have no overlapping variation, nothing explained in this x, then what would the r squared sub I be? The r squared sub I would be what? Which is the amount of variation in the ith x explained by the other x's. R squared is the amount of variation explained. R squared sub I is of the ith x. So if this x is completely unique in what it brings, none of the other x's have information in it for that x, the r squared sub I would be equal to what? What would the r squared sub I be equal to? None of the variation. None of the variation in this x is explained by the other x's. That help right there to see that in the chat? 0. And so the formula then would solve out to 1 over 1, which means that the variance inflation factor is 1, meaning that the variance is not inflated. What is the highest variance inflation factor? Variance inflation approaches what value? What does variance inflation factor approach as r squared sub I gets very high? As r squared sub I gets very high, variance inflation factor approaches what? put it in the chat for you, see. As what does it approach? So you can plug that formula into R or check it out. As R squared sub I gets very high, variance inflation factor approaches infinity, because it's how much have you inflated your uncertainty, and if the x's share a lot of variation, then you have more and more and more and more and more and more uncertainty. You want your R squared sub i's to be very low or high. Now I'm going to do a poll. R squared sub I and you want R squared sub I to be low, or you want it to be high. So let's take the poll right here. Go ahead and try the poll real quick. You want R squared sub I to be low or high? Does anyone want to say, and good answers so far? Does anyone want to say what R squared sub I is? Might not even have to ask that because it looks like people know. Good job. R squared sub I is the shared variation in your x's. And I want to say a huge thank you. I think people are listening, taking down notes. Since it's the shared variation in your x's, 100% of people got it right. You want it to be low. Now you want R squared to be high. That's the R squared of the model. But that's the amount of variation in y explained by the x's. But the R squared sub I is the variation in an x, the ith x, like your first x, your second x, the I becomes 1, 2, 3, whatever x's you have. You want that to be low. How many R squared sub i's are there for this model? Really quick question. How many R squared sub i's are there for this model? How many R squared sub i's are there for this model? How many R squared sub i's are there for this model? How many R squared sub i's? This is for every x. The I stands for the first x. There's 3, yep. 3 x's, 3 R squared sub i's. That's what the R squared sub I is for the variation explained in the first x. The one with the least amount of multicollinearity was Greek, because that has the lowest, but they're all ridiculously low. There's really no multicollinearity here. So, Diplomat Chicken, Friendly Bunny, Wise Griffin, Sturdy Shark, and Diplomatic Bobcat. Next question, let's do it. What does the p-value for the interaction mean? Ooh, what does the p-value for the interaction mean? First off, you got to find it. What does it mean? P-values for interaction have the colon for them, and you'll notice the last one is the p-value for the interaction, and it is between 2 quantitative variables. So the coefficient of weight depends on the coefficient of GPA. For higher levels of weight, GPA will have a wetter coefficient. And the short answer is it does bring new information. If weight is at higher levels, for higher levels of weight, GPA will have a wetter coefficient. I'll actually make it weaker. They'll have a higher, right? For higher levels of weight, GPA will have a higher coefficient. It'll actually go towards 0. It might go through 0, but notice how GPA has a negative coefficient to begin with, and then it's actually going to make the line go more positive. So it's actually going to make it weaker. Interesting right there. Does everyone see that? GPA has a negative coefficient to start, and then at weight 100, we're actually going to subtract 0.23 from it. And at weight 200, we'd subtract about 0.48 from it, decreasing the coefficient of GPA because the interaction is positive. It starts like this, GPA, and then it gets more negative. Any questions on this right here? But this is a quantitative interaction where we see it does bring with it new information, unlikely by random chance. For higher levels of weight, GPA will have a more positive coefficient, but that actually goes towards 0 because GPA starts out negative to begin with. Can you explain that again? Look at the coefficient of GPA to begin with. It's negative. The interaction is positive, meaning as weight increases, the coefficient of GPA will start to go towards 0 because it's going to become more positive. So what you can do, we'll do a quick example with this. Oh, I could see Peter writing a very hard question like this. Solve the implicit line model. Okay, you ready? I can see this being a really hard question on the test. Solve the implicit line model for a person who weighs 100 pounds. Okay, your chance right here. Go ahead and start solving it. I'm gonna show you how to do it in a moment. Let's see if you can solve it. Two decimal places. Oh, and someone try to solve it. Don't worry if you get a wrong answer. Oh wait, Jacob might have it. Jacob, close. Make sure to reduce it. So Jacob, really good answer. Thank you, Jacob. Looks like Jacob's done most of it. I'm gonna put back in right here, wait. And Jacob, great job. You might have been solving it before I said they are not Greek. So what Jacob's done is Jacob has gone here. I'll turn off the music. So Jacob's gone in and done. Good work. Yeah, no, I added it afterwards, so it's my fault. You go this plus, and then these are the coefficients. These are the names of the variables. So you notice Jacob's just added in the coefficients. And so we're showing what Jacob did right here. Thank you, Jacob, for writing this all out. And then these are the names of the variables. So you just start adding in the names of the variables here, one by one afterwards. Does that make sense? Hopefully to see it on the screen. But we won't get a solved value yet. The implicit line is a line where we can use it to solve for values because we would still need to know someone's GPA to make predictions right here. So the implicit line is when you plug in the values right here. I noticed there was the second categorical X. And so now we go in here and we're going to plug in that somebody has weight 100. And notice how this will change the intercept now. And somebody is Greek, not Greek, yes, so we'll put 0 for that. Because indicator variables can only take on zeros or ones. And then we solve this right here. So notice this right here, the interaction will change the value of what? The interaction, and that might be it there, Tom. Let me double check. Oh, Thomas, you might. No, Thomas is right. Great job, Thomas. Thank you. Let's make Thomas a mod. Thomas, that does look correct. I think I was carrying too few decimals when I did it originally in my head. Notice that the interaction, the last portion of it, changes the what? The interaction, the last portion of this, if you look at like terms on this, the interaction is going to change this. And the indicator variable, which is this, that's not the indicator, sorry. No, it does do it. This is just going to change these. Does that make sense? I think Thomas has done it right there. It's not. Which one's not? I think you have it correct, right? If you just solve the values right there, the things in pink will become the new intercept, and the things in green will become the new slope. So solve this out right here and you will get it. Simply multiply and then combine like terms. Notice that GPA is the only one right there, but try to solve this. Know how to write out implicit lines. Really good example right there. Good stuff, great questions, and good practice being able to write the implicit lines. So good stuff. Okay, next question. Diplomat Chicken, Friendly Bunny, Wise Griffin, and Dynamic Bobcat, Blue Hen, great work. What does the following show? What does it show? Oh my gosh, what is this? This is the very end of the semester is what it is. Hey. Waking up. Okay, a lot of people said the end of a stepwise selection. So this output right here, very important to understand what's going on, is right now, this is the current what? Just read it off from the output. That is the current what? That is the current what? Right now we are currently at what? That's the AIC. Well, it's direction forward. Sorry, I might have mispointed. We are currently at an AIC of this, which means how close we are to the truth. It's not like a literal distance, but it's a measurement of how close our model is to the truth. Now, this is our current model, and it's height tilde 1, which means we are currently using the what model. It's height tilde 1, which means we are currently using the what model. So it's height tilde 1, so we are currently at the naive model. Now, at the naive model, you can go forward selecting and inputting variables in. The saturated or full model or complex, you can call it saturated, all the variables in, full, all the variables are in, full, or complex, a lot of variables. You could go backwards. You can always go both directions too. The model will put in gender to predict height right here because gender reduces the AIC the most. So this is what we are considering, these two steps right here, either put in gender or weight. And at the end of a step procedure, you will see none at the very top of this. So this is the start of a step procedure where we are starting with the naive model. We are allowing ourselves to go as low as the naive model and as high as the complex. The model will input variables going forward. The current AIC to start, which is how close we are to the truth, is about 18,069. And the model is currently the y variable with no x's. That's the naive model. We are going to input the gender variable, and that will lower the AIC for the model. Any questions on this output right here? I know it's one of the last things we talked about. Why is this a naive model? Just the format y tilde 1 is the naive format. It's what we stored into it, and that's just the way we write it. Good question, Jack. William right there. But that's just the way it's written. Like that's just how I write the naive model. So it's the naive model because it says height tilde 1. So that's where we are currently at. We are going to input gender, and we'll no longer be at the naive. Everyone. I want to be 100% by the middle of this week. 100%. I'm going to take a COVID test. If I come in Tuesday, which I plan to, I hope to see my students one more time. But if I come in, I'll have taken a COVID test if I'm going to be around students. So I'm going to do that to make sure COVID. So I'll probably take one like Monday or something like that to make sure. That's tomorrow. Oh my gosh. Okay, next thing right here. Diplomat Chicken, Friendly Bunny, Wise Griffin, and Dynamic Bobcat, and Brave Yeti. Hey, Brave Yeti, how you doing? Which way do we interpret height? Which way do we interpret height? Now, what do you notice in this output? Look at the way it's coded. Look at the way it's coded right here. It's a GLM, family binomial. You are doing what kind of regression right here? You are doing what kind of regression? A lot of answers right here. You are doing what kind of regression? I actually show this in R. You are doing what kind of regression? It's GLM. You are doing logistic. Don't worry, this is our chance to learn and practice. And let's look at a simple logistic right here. Here we are with logistic. Can anyone give me the interpretation of the coefficient of height? Can anyone give me the interpretation of the coefficient of height? Try it a moment in the chat right now and interpret it. Don't worry about getting it wrong. I ask these questions for a reason. I'll give you a hint by showing you a graphic. We will use it for that purposes, yes. Technically, no. In our class, yes, but GLM with family Gaussian, which is the default, can do linear. That doesn't work with some of our functions. So in our class, we will use it for logistic. but it can be used for linear and other things beyond like Poisson, I think. You can do more families of models. GLM stands for generalized linear model. The LM is just the linear model, just the Gaussian, which is the linear normal curve. Gaussian is the normal curve, the Gauss. Kind of, Matthew, very close, Matthew. That's all right there. Good job, Emma, right there. Kind of. Great. Lisa right there, that's the answer I like the most. So with this, be careful. Two things to point out. One, never think of it as cause and effect, because if I get taller, does my probability of male change? Like as Brian gets taller, his probability of male increases. As Brian gets taller, his probability of male increases. Is that the way it works? As Brian gets taller, his probability of male increases. Is that the way the world works? I'm going to be more likely to be male as I get taller. As Brian gets taller, his probability of male increases. No, I'm either male or not male, right? So it's probability of male is not going to increase as you get taller. Here's what does differ. Two people or individuals, like if we talk about in the broad sense, individuals with higher heights would have a higher probability of being male right there. Individuals who are taller have a higher probability of male, and male is the level of interest for the logistic categorical Y we are predicting. So two individuals who differ in their height by 1 inch, the individual who is taller is more likely to be male. And we know this from the output because the coefficient of male is positive, or the coefficient of height, the coefficient of height is positive. So with the coefficient of height being positive, that means it's sigmoidal up. The logistic curve has an upward S shape to it. And so here's the thing we don't do in logistic. We don't interpret the size of the coefficient, like the numeric value, because it's not constant. Because the increase, while it's always positive, differences among the curve are more sharp towards the center. Does that make sense, Emma? And good answers, everybody. We don't mention the coefficient in logistic because the differences are not consistent throughout the curve. Small differences down here between individuals who differ by 1 inch, large differences here in probability of male, where over here the differences are smaller. The 0.7 is not something we mention. We only mention, good to see here, Thomas, from 474 coming up next. We only mention the positive or negative nature of the sigmoidal down, negative, or sigmoidal up, positive in logistic regression. Also, we don't make it sound like cause and effect, where if someone gets taller, they're more likely to be male. It's just individuals that are taller are more likely to be male. I'm mildly lost. Could you say the interpretation again? Here's the exact A+ interpretation. Two individuals who differ in their height by 1 inch, we would expect the individual, or we would predict the individual who is taller to have a higher probability of being male. It will be recorded. So two individuals who differ in their height by 1 inch, the individual who is taller has a higher probability of being male. A more simple interpretation might be individuals who are taller receive higher probability or are more likely to be male. Individuals who are taller are more likely to be male, which makes sense. Does that make sense right there? Individuals who are taller are more likely to be male. Doesn't mean they are, just they have a higher probability. So good questions right there. Continuing forward. Awesome. We have Diplomat Chicken, Friendly Bunny, Wise Griffin, Eager Glider, and Sturdy Shark. It's the 474 supposed to start at 1. Kind of. We got a little bit behind, and we'll be finishing up this one here soon, so we'll be starting 474 pretty soon. Which of the following are true about R squared adjusted? This is also a good review for 474. What is true about R squared adjusted, which you see over here? We've only got 3 more questions after this one, I believe, so we'll be starting pretty soon. Good to see your Jai. R squared adjusted. R squared adjusted is R squared adjusted for multiple variables in the model. So think about this. Your lowest R squared is 0, and R squared adjusted is R squared with a penalty on it. So it's penalized R squared. And so R squared adjusted, all these things are true. It's R squared with a penalty on it. It can be negative, and it's a fair way to compare models because it's R squared adjusted for how many what's are in the model. So the weight of the penalty is directly associated, like we penalize models more when they have more what's in them because they have more of an advantage to explain. We penalize larger models more. It doesn't mean they're not the best models. They'll just get more of a penalty and more of an adjustment. So R squared adjusted is R squared penalized And the larger the penalty is due to there being more what's. R squared adjusted will be less than R squared. There is a technicality when R squared is equal to 1, then R squared adjusted and R squared are the same. That is a technicality, though. And R squared adjusted in all other instances will be less than R squared, and the amount of variables directly relates to the size of the penalty we input onto it. So there we go. Good questions, good answers. Great job, William and Emma, and good to see everyone here. We got Diplomat Chicken, Friendly Bunny, and Wise Griffin, Sturdy Shark, and Diplomat Bobcat. Next question. Someone creates a regression model using months of the year. How many indicator variables are there? Nice and easy question. Good review to round things out. How many indicators? So repeat again, indicators are used when you have what's. Indicators are used when you have what's. Indicator variables are used when you have what's. Categorical X is specifically. Oh, Andrew, you'll tell me which class, but we did so well in all of our classes. There might be one, I think 320 got max. Categorical X is great job. So let me know which class you're wondering about. But man, every class did so good. Even my 201 broke 90% for the first time in forever. 320 got max extra credit. I sent the email, check it out right there. 320 got max. They got the 10 points on the final. What? Petrie said that because he was like, I want responses, and we got it. And then 201 had an amazing response rate, which Terry approved a certain amount of points. Each class has different things by weighting, and we can always curve things, you never know. But huge thank you to all the students who did the TN voice. So thank you, thank you, thank you. Pretty easy one. If you're wondering, 12 months of the year. I'm holding another 5 down here. 12 months of the year, 12 minus 1, 11 indicators. What is the reference month of the year and why? The reference month of the year is this and why. The reference month of the year is this and why. What is the reference month of the year and why? April, because it's first alphabetical. This is for categorical X's. April is the first month of the year, the reference month of the year. There you go. Okay, 2 more questions to go with Diplomat Chicken, Friendly Bunny, Wise Griffin, Sturdy Shark, and Eager Glider. Here we go. Which order should we use? Oh, we did some of these on review day. You gotta be quick on this one. Oh, that's a tough one. Wow. I think I might have a small, I'm double checking this. How do we know which order to use? How do we know which order to use? How do we know which order to use? Largest minus 0.05. And a 0.005 though, 0.005. And I think this is so close that I must have given it to it and made a tough call right there. That's a little bit mean. I don't like that. So, was someone in first and you're no longer in first? We should give out 2 prizes. We'll give out 2 prizes. I'm gonna give out 2 prizes, 2 $20 gift cards. So if you were in first and you lost it, let me know. If you were, I'll look at the leaderboard and you're like, hey, this was me and I lost it. So one more question, because this one's a very, very technical one. So here's the steps if you're wondering how to do this. Find the largest R squared adjusted. Check out last lecture, which is also posted on here. What is the largest R squared adjusted on here? What is the largest R squared adjusted? Order number what? Which one's the largest? Order number what? The largest R squared adjusted is order number what? Order 6. So we type this in right here. And then we subtract, this is the second step, 0.005. So this is the standard by which we got to meet. Now here's the thing. It's usually the lowest AIC2, right? It's usually our AICC, which is AK's information critically corrected. So you could have just kind of glanced at that too. Which don't do that on the test because that's not the direct method. But here's the thing. I noticed as I was solving this in my head that the correct answer was not one of the choices. Because the technical correct answer, you know what? let's give this person the $20 gift card, whoever answers it first. The technical correct answer is order number what? I'll say your name. I'll see it in the chat first. I'm going to show it on screen. William got it. It's order number 4. So William got it, just so people can see, so they think I'm not, no one's like, you can see on my screen, William said it first because it might look different on your screen, but William said it first right there, order number 4. William, that is the technical right answer. And great job everyone else answering that, showing you know how to do it too. That is the technical first one that beats this. So you go by the first, doesn't beat it, second doesn't beat it, third doesn't beat it, and fourth is the first to beat it. Make sure, William, to email me, Amazon or Starbucks, whichever one you want. Starbucks gift card for you. So when we're giving an extra right here, also the first place we're giving one. So check that out. And great job, William, right there, being so quick, being like it's 4, showing that you know how to do this. With this right here, I'll do a separate one in a second too, so we can do one more practice on this. Notice that model 2 is super duper duper what to our threshold. So it's like, super close. None of these things that we teach you are like, it has to be this way, because all models are what? Model 2 is so close to the threshold. All models are what? Wrong. All models are wrong, but some are useful. So maybe we go with model 2 here. And I think that's what a lot of statisticians would do, is that they would see this jump in R-squared adjusted, this leveling off, and they'd be like, you know, and AICC is the lowest. A lot of things point to model number 2 if you go for a more advanced holistic view on this, rather than I have to go by this cutoff. So I do ask you to question everything we teach you, to be like, is it exactly 0.005? Who said that? Like, well, I mean, it's kind of a good standard to use, but maybe you could use the 0.006 cutoff. It is your standard that you should hold to and try to keep to, but you could also weigh in favor of AICC. Now, why do you think model 1 is so different from model 2 and beyond? Look at model 1 and tell me, why is model 2 the correct answer for the test? And Emma, great answer right there. If we say use the 0.005 standard or follow the procedures, model 4 would be the right answer. Of course, it could have some like written thing being like, well, we might choose model 2 because it's so super duper close. What do you notice about model 1 versus model 2? Model 2 has a much wider AICC, which is how close we are to the truth. Model 2 has a much wider AICC. Lower AICC, right? Which lower AICC means closer to the truth. AICC we want to be as small as possible because it's how close we are to the truth. It can go as low as negative infinity. Also has a higher R-squared adjusted, which is after we penalize ourselves for multiple variables in the model. I'll do one more right here where we can get the right answer. Also check out last lecture, which is posted for all students. The last one I taught, and it is in your link that I sent out. We're just gonna make another really quick model right here. M save into LM, height tilde weight, and data equals 1. And then choosing the polynomial order, which model should be chosen right here? The answer is super quick and super easy. Ooh, it's not. It's a close call, but it does. What polynomial order model? Oh, you can't see it. What polynomial model order should you use? What polynomial model order should you use? And the trick does work. Yep, Jacob got it. You go to the highest the highest R-squared adjusted, and then you do minus 0.005, and there's your standard. You start at the first one. It does not meet it, does not meet it, does not meet it, and does meet it right here. So make sure to go in that order right there, and we'll do one more just so people can see the process again. What's another variable in here, like num piercings, I think. So num piercings. Nope, it's not num piercings. Bless you, person sneezed over there. Num tattoos, num body piercings. Num tattoos. Okay. These are all pretty bad models, and I'll be darned, I'm glad the way it turned out. Okay, so which model should you use here? Which model should you use here? Which model should you use here? Like that. Nothing changed about this with me doing this. Step 1, do what? Step one, do what? Step one, do what? Follow the steps. Good work. People are getting some right answers. But step one, do what? You go back to the original output if you want. Step one, do what? Step one, do what? Find the highest R-square adjusted. Why are you done? Why are you done now? And then you subtract 0.05, right? But think about this. The one variable model, there's no simpler models. So there's nothing simpler than that. So you only look at models that are that or less complex. That's why we always start at the top and see if it, and then we go down to that model, but you don't choose a model more complex than your best one. Does that make sense? So since the one variable model, or the linear model, polynomial degree 1, is the best, well, that's it. But this isn't very good. So someone might say, I don't know, maybe you should just go with the what model. For predicting people's, I mean, rather than use number of tattoos, I might just go with the what model than even use this variable. Instead of using this, because when you look at the slope, it's not that sloped. You could use the flat line, the naive, the mean of y. So you could just use the mean, because it's only 1%. I mean, R-square adjusted. Would we have a question where the lowest ASC wouldn't be the answer? It's technically possible, but I can't promise anything. Technically possible. More than likely, they will coincide. They often do. Still technically possible. So just because people measure things differently, I'd use the methods we explain on how to do it, and then have a backup that you know the AIC should be pretty low. It doesn't mean it will be the lowest. It oftentimes is, but good questions right there. Thank you for asking. Last question. Gosh, Diplomat Chicken, Friendly Bunny, Wise Griffin, Sturdy Shark, and Dynamic Bobcat. Here we go. Which value tells us the model is statistically significant? Too easy. Too easy. Oh my gosh. Know your output. Know your output. I don't know why I have so long on this. Let's ending on such a positive note. Congratulations to those who won. We're going to start 474. I'll send a reminder here in a second. I'm going to try to go for at least an hour, maybe 30 for 474. Go home, eat some lunch, relax, drink some tea. Shout out to my coworkers who said get some tea with some lemon, some honey, and some ginger. Ginger tea with lemon and honey has been my best friend. It's the final format, all multiple choice or some fill in the blank. I'll have to double check with Petrie. He's finalizing it. Huge shout outs to Petrie. I think we're doing pretty much multiple choice. Don't quote me on it too much right there. But it makes grading for us way easier when we have it when it's multiple choice. So pretty sure. It's gonna be like the midterm. That's what we like to say. So it is the p-value. I'll double check with Petrie, but I don't think there's fill in the blank because then, or there will be fill in the blank probably. Excuse me, William, right there. There will be fill in the blank like numeric response, but there won't be like portions that are not graded. So it'll all, as far as I'm understanding, because I've been talking to Petrie about it, and Petrie's recovered, I think, yay, we like that. It'll all be auto-graded, but there won't be like long interpretations from what I understand. So that's awesome right there. Well, in first place, we have Diplomat Chicken. We've got some Kahoot t-shirts for other people if you want. I still got more than enough. Swing by an office, get a Kahoot t-shirt. Is it multi-select with drop-downs? Could be that right there. Just like, I'd say midterm format, that's what to expect. Expect midterm format with multi-select, with numeric entry, but no long response that had to be graded afterwards. Diplomat Chicken, make sure to email me, Amazon or Starbucks, let me know. $20 gift card for you. Great job. Man, we got time for some 474. If you're taking 474, you can hang out and watch what's going on. We're about to hit the 3-hour mark. So, 3-hour mark in. This is why I wanted to recover one day more, and I am sounding a lot better. But I was like, I want to recover one day more. Hey, Jesse, bye. Bye, Emily. Bye, Elisa. Bye, Emma. And good to see everyone here. Good to see you. People are joining in. I know, right? So I was like, one day more will help out. And one person was like, well, we got games. And so I was like, oh, you know, it coincides with people. There was a request to move it. And I was like, you know, I just woke up yesterday and I was feeling kind of meh. Not bad mad, but I've been coughing more at night, which sucks. Like a bummer, you wake yourself up and you're like, oh. don't want to get my wife sick. So I go upstairs and like sleep on the ground. And then my hips are hurting. My hips are hurting, and my back was hurting last night. And I was like, "Oh, this is great." So, anyways, we're figuring it out. Bella, good to see you there. I know, right, Thomas? I think you're the one who asked, and I was like, "Well, there was a request," and I was like, "Well, that worked out." Find out the announcement right here. Worked out nice and perfectly for everybody. Okay, we're gonna send out the announcement. Thank you so much, everybody who's here. Go Vols, glad we won that game. Who do we beat? Man, it's at times I don't even feel like I have a cold, which is so exciting. I'm gonna take a COVID test. Make sure I don't have COVID when I come in on Tuesday. Don't get anyone sick. Who that one? On send announcement beside me. Who tomorrow? Like I said. Illinois. Well, who's starting? Click here. Awesome, I'm glad we won. Sorry, clearing on my throat. Awesome. I swear it sounds a little echoey. How does the audio sound for everybody right now? Does it sound echoey? Does it sound good or does it sound echoey? Like my audio with this microphone. I'm used to the Shure, but I think we're doing the right microphone. Sounds good? Thank you, Matthew. Okay, good. Everyone likes it. Okay, let me get the Kahoot up. We used to have stellar audio because I'm gonna try to mute myself. Noise. You don't hear any echoes? I like that. I appreciate that. Kahoot.com. My 80s. Kahoot logging in. Good, no echoes. It might be that sometimes the earbuds do weird things. Last Kahoot of the day, 474. Now I want to point something out. When I reviewed on Friday, I looked directly at the final. Is everyone hearing this? When Brian reviewed on, did I say yesterday or whatever? When I reviewed last week, no wait, yeah, it's last week because it's Sunday weekend, so whatever it is. Last time I reviewed, I was looking directly at the final, and I would say we did questions that were about half of the final. Now, I can't tell you everything that's on the final, but I literally did. I just want someone to acknowledge this in the chat. I looked at questions on the final, and I came up with questions that were about 50% directly from the test. There's things on here today that are pretty much like the test. I'd say maybe you get another 20, 30% here today. Like of a non-overlap, of non-multicollinearity. This will be recorded and posted. But what am I trying to tell you if you haven't seen? It sounds like a trick, I promise not a trick. If you haven't seen it, what should you do with last class? If you haven't seen the class, where's the video? The video, I can't post the link here, but the video for the last class was sent out as an announcement. Go watch, and it's not on Panopto though. It'll be here, I'll show you where it's at. Don't post the link though, because this is a public video, so they're unlisted videos. Class today, here's the under the weather. I'll go show it here and then we'll start the code. This is the link right here. So there's the link right there. We need to watch or rewatch the last class. I would highly suggest it. And be able to solve, when you see me solving those questions, be able to solve those questions. If you can solve those questions, good to see your meat. If you can solve those questions, you are on a very good track right there to solve for the test. It's not everything, but it's a good portion. And now we're gonna hop in here and take a look. Start our Kahoot. Okay, so definitely check out last class. I'd say between this and last class, you probably have 70, 80%, somewhere in that range of pretty much exact questions. I mean, not like word for word verbatim, but you know, like it's like a twist of the wording. Yep, recorded, totally recorded. Everything here is recorded. You can watch it later, just clicking the same link. Okay, joining the Kahoot. Got Classy Fox, Amazon Goat, Stellar Bunny. I wonder if people spin for bunny names, knowing I love bunnies. Captain Gator. You totally look like a Captain Gator. Looks like a Star Fox character. Totally Star Fox Captain Gator right there. I'd be like beep 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 beep. I did that for my wife, and she didn't get the reference. We were in the car, and we heard like a noise or something. I was like, and like I'm like, oh man, I'm a '90s kid. I guess that's what I am. I'm being. If I was born in the '80s, I'm a '90s kid then, right? Because I mean, I was born in the '80s, but that's not like. I watched Stranger Things, and I don't really like. I remember that time, but Stranger Things, I think, being set in the '80s, like I was very young in the '80s. Like I was a kid. Like I grew up in the '90s. Like I'm all about like Nickelodeon and Nintendo, but like Stranger Things is like Atari and arcades. Like I didn't have that arcade culture. I mean, I went to arcades growing up, but like it wasn't like arcades were like the biggest thing. I mean, they were cool, like putt-putt golf and stuff, but it wasn't like oh my god, the arcade. It wasn't like, whoa, you got an Atari. Like we were like, you got an Atari? That's old. Like even back then we thought that was old because Nintendo just took a huge leap forward. Like Atari, even though Atari was like 7 or 8 years old, it's like I was like, I just got this a little while ago, and we're like, that's super old, man. So when you're like 13, and you think back to like 8 years ago, you're like, I was a baby. Now when I'm like in my 40s and I think back 8 years ago, I'm like, man, that was like yesterday. So putt-putt is fire. Yeah, I do like some putt-putt golf. Go out, do some putt-putt golf, get that hole in one. It was LAN parties. Yeah, LAN parties. We did that in college. Like we didn't set up. Yeah, that's 90s right there is LAN parties. Were we playing like Quake or probably Quake? Was it Quake on LAN? Quake was a big LAN game, I think. Wonder what else you were playing, Andrew. Let me know in here. But I bet Quake. I'd get back to good money was Quake. Halo 1. Oh yeah, we played Halo 1 in the dorms, and the dorms had a LAN here at UT, so you could just literally be, and it was instant. Toontown, Halo, Quake, Counter-Strike. Oh yeah. Oh my gosh, why did I not think Counter-Strike, CS, Counter-Strike, Global. What's it called? Yeah. Yeah, Halo LAN parties were all-time gaming for me. Yeah, man, I miss Halo. Halo 1, when there was fall damage, you had to actually like crouch. You would hit the ground, you'd crouch real quick, and it would negate a lot of fall damage. So there was a lot of like areas in the game where you could just like jump off really high things. You know, like, let's just take away fall damage. Whatever. Okay, we'll get started here in 1 minute. Oh, 5-shot pistol. I think if you did like, was it like, you could get someone in 3 shots or something. Start a 1 minute timer.
1 minute.
1 minute till start. Yeah, I think it was 3 shots if you really go with the pistol. I think. Is that right? It'd be like 1-2-2 or something. Red might remind me. Then you just get like get the sword. The sword was even in Halo 1. You just get everyone just insta wins. It was it in Halo 1? It was in Halo 1, right? Rocket launcher, fun stuff, Blood Gulch. Halo 3 BR could be 3 to the chest and 1 to, there you go. Is that I think with BR, what is BR? I think no, I can't remember that. I played a little Halo 3. Halo 3 was good. MLG mode was 4 shots. I like how everyone, we're talking all like the LAN party Halo and all those trying to figure out. Halo was such a good game. So shout outs if you like games right there. Anyone want to drop their favorite game in the chat? Right now we're playing what is it? Oh my gosh. Zelda, playing the Zelda games with it's the Dynasty Warrior type games. Calamity, Age of Calamity, Zelda games. I can't think what they're called, but they came out with Zelda, Hyrule Warriors, Age of Calamity, 007. Yeah, man, some GoldenEye 007. That's some N64 stuff. Black Ops 2, Call of Duty Black Ops 2, good stuff. Rocket League, classic. I think they just came out with a new season of Rocket League, right? I play like Binding of Isaac. I just bought Resident Evil 2, the remake. Gonna play that. Resident Evil 4 remake was astounding. The COD Zombies. Yep, Call of Duty Zombies right now. Yeah, I've heard a lot of good stuff about that. But man, Resident Evil 4 remake, that probably got some Game of the Year stuff. Really good stuff. Well worth it. Okay, well, break's almost here. So if you want to play some video, last game I enjoyed was Cuphead, was it? I think it's the Hearts one, but Cuphead's really good. I played a little Cuphead. I should play it more. I should just finish it like I did. During COVID, my friends and I farmed all the GTA heists. Well, then GTA 5 coming out. All the outrage over that, so... but man, GTA's been around for a while. I played GTA back in high school, and then Melee 2 fun. Oh, Smash Melee. Heard new event, Avatar game came out. Oh, interesting, the new Avatar game. Yeah, might be really good. Gollum came out this year, not a game of the year. Kong came out, not a game of the year. So lots of good stuff. Anyways, who's ready to Kahoot? I need some I'm readies. We're gonna get serious right here. I'm gonna well, I already mentioned some other stuff. Who's ready for Kahoot? 4 years of Apex Legends, good stuff. I hate it, but I love it. I need some I'm ready's in the Kahoot. Sir Bad Steve. Ready, but I need I'm ready. I'm ready. Woo-woo. I'm ready right there, says Thomas. In 3, 2, 1. Brian's break is over. It's time for Kahoot. Get ready right here. Gonna try to make sure you know a few things that are gonna be on the final. And let's do it. Make sure to check out last class where we went over some more stuff. If our model has an accuracy of 0.902 and a standard deviation of 0.025 on the accuracy, what is the worst model that works just as well? This is called the one something rule. The one something rule. And accuracy is the percent of time we accurately predict the truth. So you want accuracy to be high. High accuracy means we accurately predict if something's the yes class or accurately predict if it's the no class. Higher accuracy, the highest accuracy is 100%. And what's interesting is you can't really get accuracy below 50, because if you had a 0% accuracy, then you'd pretty much be right, because you'd get things wrong. You don't want 0% accuracy though. So the general worst is about 50% accuracy, where you're half the time wrong on a binomial prediction. Well, we're talking about the one standard deviation rule right here. The one standard deviation rule states that any model within one standard deviation is virtually identical. So you would take this 0.92 and what the standard deviation, which is the amount of uncertainty we have in the accuracy. You would what this. To find a model that is worse but similar, you would take this and what this standard deviation. Someone will say it, but then you'll see it. You'd subtract it. Because the standard deviation is the amount of uncertainty we have. So we're saying we think the accuracy is about 0.92, but we could be off by about 0.25. Now, this uncertainty comes from the cross-validation, which is an estimate of how we will do, and the estimate has within it uncertainty. So any model that is predicted to have a accuracy, if we're fitting on accuracy of 0.895 or higher, is virtually identical. Now, we said this in 320. All models are what? Hence, we could pick a model that has this and think, well, it might be good enough. All models are what? Our best model has a 0.92. But then a model that is just as good could have 0.895. All models are wrong. So we're going to get a model that's wrong, but this model might be useful. So we can kind of look at models and pick between, and then we see how it does on the what. The most important thing you need to know about this class is after picking our model, only then do we try, and only do we try one time and one time only, do we then look at how it does on the what? On the holdout. Because then we say, okay, here's how I think it will do. The model I want, does it work? That's when we test it on the holdout. The final check, don't fit to your holdout. You're just fitting to the holdout when there's no point of checking it because you've already made it. Royal Chicken, weren't they leading last game? Stellar Bunny, Bright Squid, Captain Gator, Dr. Yak. What if they stayed over between games? I don't think, because I reset it, but that'd be pretty funny. Like 320 winner and 474 winner is the same person. Here we go, next question. How many models are made right here? Seems like a tough question, but I promise it's really easy. We'll talk about what these things mean right here, but this is a forest model using an expand grid with mtry with a concatenated vector of 1, 4. So how many models are being created? And what does this mean? Well, a forest is a whole bunch of trees, where the trees are bagged, where they have different X's and they have different rows. And only a few people got, well, I mean, about half the class got it right. That's all right, and almost exactly half. I like that. Good job. We'll do a little wow right here. I like that. So with this right here, what does mtry stand for? What does mtry stand for? Mtry is the amount of what's that'll be tried for each tree created. What does mtry stand for? When you make a forest, you need to tell it, not quite models, good answer right there, not quite models, but the amount of variables. I don't know why they say M, predictors. Great job, Sir Bad Steve, right there. The amount of predictors, and Emma has it too. Mtry is the amount of predictors which are auditioned for each tree. So an mtry of 1 means only one X will try to create this tree, which is kind of interesting because then that tree is very dependent on that X. And then an mtry of 4 means 4 of your X's are randomly chosen. The highest mtry possible would be how many X's you have. So you can't have a higher mtry than the amount of X's, and you can't put in a lower mtry than 1 because you have to have at least 1 X. We're not doing the naive model here because the tree won't split. And the amount of models that are created right here is 2 because the expand grid only has one thing in it. It only has the amount of x's. So we are creating 2 different models and we'd pick between these. Any questions about forests right here? What mtry is? Forests are a whole bunch of trees that work together to make predictions. Mtry is the amount of x's or predictors that are used. And the expand grid right here only creates 2 models because there's only one tuning variable. So the tuning variable is the variable by which we are trying to optimize our model to see if we can tune it to a certain way that we get the best predictions out of our model. Question? Good stuff. Why mtry? Why not like ktry? Because usually k means variables. Stellar Bunny, nice job. If you have mtry 1, 3, 4, then it's 3 models. Great job right there, Andrew. That is true. Captain Gator, King Squid, Silver Frog, and Lovely Pony. Next question. Let's do it. A leaf in a partition model has the following y values. Compute the Gini. Ooh, got to disappear. Compute the Gini coefficient. I might be right back. I'm going to go grab a chair real quick. That's it. Chair. Is this going to work? I don't know if this is going to work, everyone. Oh, my gosh. Okay. No, this might not work. It's not high enough. My leg got a little bit tired right there. And very few people got it. So the Gini coefficient. The Gini coefficient. I need to see how to compute this. And I almost feel like there's an error here. I'm trying to think. Oh, the Gini is impurity. Okay, that makes sense. So it can't be. Okay. So let's show how to compute the Gini. And let's compute it. You ready? So what we have to do, I'm trying to go to Word. And the Gini coefficient is going to be 1 minus, and then the amount of A over N and squared of this value, and then plus the amount of B over the amount square of this. So that should be it right there. So if you have, oh, still the same thing right there. This chair might not work, it's way too low. Oh, let me lower my desk. Desk? Okay. Oh my gosh, it's working. Now if I reappear, you won't be able to see me. Whoa, I feel much better now. Hey everybody. Okay, so think about what you have to plug in right here. What values would you have to plug in? What values would you have to plug in to find the Gini coefficient for this? So think about this right here and tell me what values you're going to have to plug in. What values? Basically, you can go straight to that if you want. And if you go right here, we're going to have to plug in the amount of the one group is 1 out of 4, and this is 3 out of 4 right there. 1/4 and 3/4 right there, respectively. So now when you go ahead and solve this, you're going to get this is 1/16, and this is 9/16, and that's going to be subtracted from 1 right here. And when you subtract that from 1, you're going to get 16/16 minus 10/16, which equals to 6/16. Number one thing, please do this. Watch or review classes. Write down Does everyone see this? You need to write down every formula you have with an example. Write down every formula with an example of how to do it. So like this example here, which solves out to 16/16, which then solves out mathematically to this, you need to write down every formula with an example. Does that make sense? What should you do? Put it in the chat to remind yourself. Before taking the test, you should look at and look through the notes and find every what and have a what. So have what. Go through classes review, because you get notes. So have every formula written down with an example of how to solve it. So even a small thing like this, where in this example, we've done a lot of notes today. Right here was because the data was no, 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 yes. Because that's what it was, we just input right here the 3 no's, and then we input the 1 yes, and the total is out of the 4 right there, and that's how we solve it. What is the worst Gini for a 2-class prediction? The worst Gini coefficient for a 2-class prediction is what? The worst Gini for a 2-class prediction is what? Which is impurity. The highest impurity for a 2-class prediction is what? 0.5. So that would eliminate an answer right here. It would eliminate this answer. Don't worry if you said those, but 0.5 is the highest impurity. 0 is the lowest. So you're just between these and 2 right now. So good stuff right there. And next question. Stellar Bunny, Silver Frog, Captain Gator, King Squid, and Eager Giraffe. Next question. Which of the following allows us to analyze categorical variables? Ooh, I like this question. So which of the following allows us to analyze categorical variables? Really only one wrong thing in here. Which of the following allows us to analyze categorical variables? Categorical variables. So linear regression has the condition both variables are 2 quantitative variables. Now there's ways around that with your x's, but linear regression is a quantitative y. So very important right there to know linear regression is quantitative y. Partition models are also classification trees. So even a forest is a type of partition model right there. So that is going to be, it can be categorical or quantitative. And gradient boosted models are also allowing for categorical or quantitative. Now, in what way would you know when something's being created if it is categorical y? Like what in this code, or I'll write over here in R. If I were to write some code right here and do something like m save into train, and we don't even have it loaded, but we can go y tilde x or dot comma data equals my data, and then method equals glm net, and then fit control equals control, no, PR control. Then here, what way would you know this? Yes, nice job right there. And kind of Matthew. So Matthew's pointing out in the TR control, we probably need to load caret. So this will load library caret. Oh, do I not have it on this computer? I've got it on my laptop. This computer has not run. I don't have library caret? Are you serious? So many packages. I don't have caret on this computer. I reinstall R about 1 billion times. So you can watch over the multiple semesters me reinstalling R. Just haven't used this computer to do this. There we go. And now here we go. Train control. There it is right there. And now inside of here. Now notice, very importantly, what we want to do is we usually use method equals cross-validation. And then we can do right here, the number right here is going to be the number of folds, 5 folds. We could do repeated CV, but we want to do class probs. This is where, if we are doing a classification model, look right here, a logical should class probabilities be computed for classification models along with predictors. So class probs equals true. Our model will now fit on what? Finish the sentence. Our model will now fit on what type of metric to gauge it? Our model will now fit on what? Instead of doing RMSE, our model will now fit on what? Well, it's going to fit on categorical. It's for categorical data to fit on accuracy. Hey, McKenna. Oh my gosh, McKenna. What's up? I'm going to stand up. I was sitting down. I'm just relaxing. My gosh, I got out of it today. McKenna, good to see you in the chat. We got so many people swinging by and saying, hey, good to see you. I'm relaxing. I've been staying for like 3 hours. I'm like, time to, I know. Awesome. Good to see you. Say hey to the chat. Say, hey, how are you doing? Feel free to update us. So good to see you. I'm gonna sit back down. Wah! Thank you, McKenna. Good to see people here. I love it. Summary function equals toClass summary makes it so that we're fitting for the AUC now. Thank you. Shout outs to McKenna in the chat. Still a mod. Love it. And that is how we can fit towards AUC. Please ask any questions if you have it about how these models are done or what we're doing. Okay, McKenna, you can play Kahoot if you want with us here. Here we go with the next question. Stellar Bunny, Silver Fox, Classy Fox, Silver Frog, Dr. Yak, and Royal Chicken. Next question. Achieving 100% accuracy on a training subset would probably be an issue with what? Achieving 100% accuracy on a training subset or on the validation would probably be an issue with what? I think a pretty easy one. You must know this going forward in our class. I'd hate for anyone to do this and be like, yes, I did it. My data works perfect. You probably overfit. That's a really easy one right there. Great work. Overfitting, number one big problem with model building when people oversell what they have. Don't do that. Stellar Bunny, Silver Fox on Frog on Fire, Classy Fox, Dr. Yak, and Captain Gator. Next question. Which of the following describes a complex logistic regression model? Ooh. Tough one. And we haven't been doing support vector machines, so changes to the cost parameter is not something we tune on. What you're seeing here is tuning parameters. And in logistic regression, the more complex it is, the more what's it has. Yes, McKenna, you still have your hours, but the points have been, we'll throw you some points right here. Let's throw 100,000 points. I reset the points, I'm so sorry. But there's some points to get you back. But yes, and you even have the old level. Like it. Oh no, there's some points though. So with this right here, a high complexity parameter. Who can explain in the chat when we use a complexity parameter? When is a complexity parameter, abbreviated CP, used? When do we use complexity parameter? Complexity parameter is a what? We use that for what models? The complexity parameter, abbreviated CP, is used for what models? Decision trees. And when decision trees are partition models, also called partition models, have a high complexity parameter for setting the threshold for the tree for when it will split exactly. I don't know, I'm probably fine. I'm crazy. For setting the threshold by which we split the tree. So if the complexity parameter is high, that means we're saying you need, I'm raising it back up right here, you need this much to split. You need a very high decrease to split. So a high complexity parameter will lead to a small tree. Complexity parameters work inversely to the size of the tree. That's a keynote to have correctly. And great job, Julia, there with the R part. Complexity parameters work inversely to size of tree. High complexity parameter means you get a smaller tree because the tree has to work harder to split. Low complexity parameter means the tree is saying you only need this little amount to split, so it'll split more often, making more complex trees. Lots of predictors is what we do for the X's, or logistic. Silver Frog, Stellar Bunny, Eager Giraffe, Dr. Yak, and Captain Gainer. Next question. Calculate the AUC. I love these questions. I love these. And I think I got it. I mean, of course, I made these questions, right? Wait a minute. Oh, no, that's why. Darn it. Okay, I get it. Yep, okay, now I got it. Wait, really? Throw a trick? I didn't throw a trick. I feel like I have an error on this, but we'll find out. Keep going too quick in my head. Let me double check. Oh. I feel like there's an error. I feel like there's an error. Does anyone want to comment on this? Unless I'm doing it wrong in my head. going to show it visually here in a second. Oh, it is. Wait. Why was I that wrong? Wow, that is correct. No, there's no error. Gosh, that is correct. How was I looking at that wrong? My brain really just jumped a moment. But very few people got it correct. Let me show how to get it. Hey, why was I doing that? See what I was doing. 100% right. Don't doubt yourself, Brian. You made the question. So here's the visual answer. I'll show you the visual answer right here. I don't know what's that quote going to be. Gut wrenching when you get my Pearson C part one. Oh yeah, I like that. Okay, so what am I showing you right here? Oops, needs to be blue. There's the answer. Why it is what it is. Anyone want to state the math? 11 over what? Anyone want to state the math? Matthew's right. Anyone want to state the mathematics? 11 over what? $11 over what? Let me ask you this. If I change positions here, not over 7, what is the AUC now? What is the AUC now? I was totally messing up the last part and doing 9 over 12, and then I was like, oh yeah, it's not 9 over 12. 11 over 12, exactly. I was just doing it wrong in my head, and I should have just drawn it out, and I was just thinking, and I was like, oops. But now the AUC is what? Make sure these are properly ordered, but now the AUC is what? You have to have the probability going from highest to lowest, but now since I flipped the yes and the no always has a higher probability than the no class, just the way I've rewritten this now. And so now the AUC is what? The AUC is what? It's now 1 because the yes class always has a higher probability than the no class. But also you can do the following. If you put your true no's down here, so we have 4 true no's. 1, 2, 3, 4. We have 3 true yeses. Does everyone see this is a 3x4 grid? And if you have them in order, you can mark your up, ups, and your overs. And you can do it up, then over, and then up, and then over, and then tell me, oops, green, that is green. How many of those grid pieces are covered now? How many of those grid pieces are covered? Make sure to know how to solve stuff like this. You can do it by the pairwise comparison. You can do it with the up-over method, or the up-over method. If it's a yes class, you go up. If it's the no class, you go to the right. And going through the yes class first in probabilities raises the AUC curve. When you have no class, you go to the right, which is not good. The worst the AUC curve can do is a 50-50. So you usually see that line through it. So does everyone see it's 11 out of 12? If you add up the grid boxes right here, you can see you have 11 out of 12 grid boxes colored in, and that was what the AUC curve would be. It doesn't usually look as sharp when you have bigger data sets, but if you zoom in on an AUC curve, you will see like jagged nature to it where it looks jagged because it's doing the up-over method. Any questions on this? A lot of people miss this. So here's the number one thing. What am I telling you to do? This is like big advice because we're not doing every single formula today. All the formulas, all these things right here, what you're seeing right here, should you be able to create an example and then solve an example. So you want to be able to write an example like this where it says calculate the AUC and then know how to do it mathematically for small stuff. And then that shows how we understand what's going on right here, that the AUC is the probability of the yes class, or the percent of the time the yes class gets a higher probability than the no class, and then we can mathematically calculate it. So try doing small examples right here, see how to get it. Good work right there. Brian was doing his head and he was like, wait a minute, where's the answer? But don't worry if you got it wrong. Know how to solve these things. Know how to solve them. Okay, eager giraffe, silver frog, stellar bunny, royal chicken, and Dr. Yak. Next question. Which of the following does logistic regression use to measure how the model works? What does logistic regression use to measure how well the model works? Logistic regression. What does it use to measure how well the model works? Lots of answers here. What is the only wrong answer? Logistic will not use what? Logistic will not use the sum of squared errors because that is for residuals. Residuals are for quantitative models, so it doesn't use like RMSE, MASE, MAE, MAPE, all those things right there with E at the end usually are errors, and we don't use those like sums of squared error for logistic. That's not how we'll do it. Everything else can be used, misclassification. Which of these two are complements here? Like, is AUC the complement of misclassification? Is sums of squared error the complement of AUC? Which of these are complements? Which of these are complements? Accuracy and misclassification. Accuracy is the percent of the time your model accurately predicts something. Misclassification is the percent of the time it doesn't predict it properly or correctly. And with that, AUC is the percent of the time the yes class gets a higher probability than the no class. And since we've been talking about yes class and no class, that is logistic, which is a categorical Y of interest, a classification model. Eager Giraffe, Royal Chicken in the back up there, Captain Gator, Silver Frog, Dr. Yak. Next question. Which of the following represents the typical miss the model makes? A 320 question, but good stuff to know. Something we can measure in quantitative models. One of these represents the typical miss a model makes. And the words basically tell you what they are. AUC is area under the receiver operator curve, also known as ROC, but sometimes written out as AUC. R squared is the percent of variation Y explained by the variation in X, also known as the coefficient of determination. SSE is the sum of the squared error, which is a quantity of how much error there is total. Error can be positive or negative, so we square it, which is why when we do the root mean squared error, think about root mean squared error, what cancels out? In root mean squared error, what cancels? Root mean squared error, what cancels? In root mean squared error, root and square cancel, leaving you mean error, and mean error sounds like typical miss the model makes. Some people use MAE, mean absolute error. Some people use MAPE, mean absolute percent error. It's just kind of scaling it at times with the MAPE or MASE, mean absolute scaled error, turns into z-scores. I prefer to do RMSE, it's just preference. Good stuff. Great job, Lazarius, right there. Next question with Eager Giraffe, Royal Chicken, Captain Gator, Dr. Yak, and Silver Frog in the lead. Next question. Which of the following naturally uses interactions? Ooh, I like this. You don't have to worry about using interactions if you're doing this model right here because it'll do it for you. Which of the following naturally uses interaction? No need to put them in your model formula when you're doing this model here. So let's take a look. Interactions are naturally incorporated into both tree models, and tree models have forests, or if you make multiple trees, you make forests. So logistic and linear, you would have to specify interactions right there, but interactions. Next question, but the leaderboard, Eager Giraffe, Royal Chicken, Captain Gator, Dr. Yak, and Silver Frog. Here we go. Which of the following tuning parameters does a singular tree use? How do we tune a singular tree? Lots to talk about on this screen. The complexity parameter. The M-try is for a forest where there's multiple trees. I'm gonna put a link in the chat right here, or we're gonna watch an ad for a car is what we're gonna do. Put that on here. So this link right here is all the available models in Carrot. How many models are available in Carrot? Does anyone want to say? How many models are available in Carrot? How many models? Infinite, I'd like to, near infinite, right? If you go here and do our part, you can find, oh, I'm on the wrong chat. Oh my gosh. So I'm searching in our chat, where if we go right here, go our part, and you can see right there, there's caret, our part right there, and other methods, our part 2. There's even more ways to make it. Excuse me. And let's go back. Here's our part, and there's the complexity parameter right there, which controls how large the tree grows by saying the requirement for the split. One of the biggest ones is XGBoost, which has a lot of tuning parameters. Now, this might look really complex, but here's the thing. When you take a look at what's going on right here, a lot of it we've talked about. We've talked about like how big the tree goes, max tree depth. We talked about shrinkage, which is learning rate. Here's XGBoost linear right here, the learning rate. A regularization parameter. So we talked about regularization by controlling for the size of the coefficients. So these models get really complex to tune, and there's a lot of options, but this is where you can usually make the best possible models because there's a lot more room to figure out what works best. Doesn't mean it will work. It's not a one-size-fits-all. We have to be able to create different models. Does it make sense of what the last part of this class is? We are giving you different tools. Like we could have taught you distance-weighted discriminant with radial bias function kernel. So that's a discriminant analysis with weighting on the distances. I've never used that. With a radial basis kernel, function kernel. So that's how it's coming up with the equations. Yeah, fun stuff. You can change the kernel function. There's lots of ways to do this. The diagonal discriminant analysis. That one. Cumulative probability model for ordinal data. Well, we don't work with ordinal data that much, but if we do, we'd need that. Cost-sensitive cart. Use that. It's an R part though, so it looks like a tree. For classification, using packages rpart and plier with tuning parameters. Ooh, that's interesting. Got a cost tuning parameter. So there's so many different things to do, and here's what I want you to know. Know your models. Know why we're doing them. Let me write this down for you. One, know every model, like, and why we use it. Like, why are we using a tree? To create partitions, to segment things into groups, to predict a categorical Y or a quantitative Y. Know the tuning parameters. A tree has a complexity parameter, which is how big the tree grows. The smaller the complexity parameter, the less we require in a reduction in SSE or impurity, and then the tree will grow larger. The higher the complexity parameter, the more we require, and then the tree is not likely to grow, and we're more likely to go towards the naive model. Know the model metrics evaluation. If a tree is being done for a quantitative Y variable, we will analyze the RMSE to analyze the typical miss the model makes. If a tree is being done to analyze a categorical Y variable, we can look at misclassification rate, or we can look at AUC to see the percent of the time that the tree gives the yes class a higher probability than the no class. Know these metrics right here. This is probably a whole lecture. So go back and watch the lectures, maybe skim through them and write these things down right here. I can't negate this. Know the formulas and have examples. I can't understate this last part enough that there is math on this final. There is math, and you need to know the formula, and you need to know how to solve them for things like Gini coefficient, Gini of a split, sums of squared error of a split, things like that. Here's a free example sums of squared error question. Let's look at this right here. We have right here, what is the sums of squared error for this leaf if it contains these values? What is the sums of squared error for this leaf if it contains these values? I've got it. What is the sums of squared error for a leaf if it contains these values? What would be the sum of the squared error? Pretty easy because of the symmetric nature of it. Define sums of squared error. Yeah, Thomas, great job. It's 36. Yep. Find the mean. And I made it 8282, so the mean is 5. Step 3, step 2. Find the error. So now the error is going to be, this is 3 more, this is 3 less, this is 3 more, this is 3 less. Great job, Thomas, right there. Step 3, where the errors. And that becomes 9, 9, 9, 9, and then step 4, sum the errors. Now, if we're doing it for like a leaf, we might have to find the average. Make sure to do questions like that to review when you're looking at the error of a split. And we've done a lot of those in class where we went through and looked at the notes. Notes are really good examples of looking at the error of a split and which way a tree would split. So just small examples like this, if you can write it and be like, well, what would the sums of squared error of that partition be? Well, I need to find the mean of it. I need to find the error from that mean. And then I need to square those. And I need to sum them when you think about the sum of the squared error. How did you do step 2? The error is right here. So this technically would be, the math is going to be 8 minus 5, and 2 minus 5, 8 minus 5, and 2 minus 5. Does that make sense right there? Great job, Jay, and also everyone in the chat following along asking questions. But that's how we find the error. 8 minus 5 is 3, 2 minus 5 is negative 3, and then you're squaring it. So all you're really asking is how far is it away? Good questions and good practice. Just knowing how to solve things like this. Remember, have examples of everything. So if it's in the notes and we do a formula, that's my like big. You'll see the test. I'm telling you, it's got formulas on there. You need some formulas. You need some formulas. That's there's some formulas on the test, or not on the test. You need to know how to use them. Since you got your notes, have them down with examples. There we go. A cool graphic. Okay, Eager Giraffe, Captain Gator, Royal Chicken, Dr. Yak, and Epic Turtle. How many models are created when you use a GLM net with alpha, these values, and lambda, these values? Should be nice and easy. We've been practicing. We got this. How many models? So this is a elastic net regression. Ooh, pretty good, I like it. Now I want us to look at how this works. If I go here, and I'm gonna go play video games at either Putt Putt or Pizza Hut. And they have Mortal Kombat, Street Fighter, and Mario. How many different ways? And they all have they both have the games. What are my choices here? Oh man, Sweeto, well, we want you to. We're talking about video games now, so then you can play video games after you study. So how many choices do I have? Think through this right here. If this is what's going on, I could go to Putt Putt or Pizza Hut, and I could play Mortal Kombat, Street Fighter, or Mario at either place. What are my choices? And the expand grid, what's your favorite video game? We need it in the chat. What are the choices right here? Can you see it? Because once we look at the expand grid, we'll see the answer for the choices. It works the same way with the alpha and the lambda. It works the same way. So what are our choices? Apex Legends 1 already said that. 6 combinations. You'll love some Apex right there. Take a look right here. You can see Mortal Kombat at Putt Putt, Mortal Kombat at Pizza Hut, Street Fighter at Putt Putt. And you know what? If we add in the Apex right here, if all of a sudden, for some reason, they have Apex, how many choices are there now? Now they've added Apex to these places. Great job, Sweetle, right there. Looks like, oh, I thought you were saying, like, yeah, you got this. Is it making sense? Now we have 8, because now they've added on Apex right there. Now there's 8 choices at the places. But here's where it gets crazy. If there's like a food choice on our expand grid, I went to the wrong one. I went to go there. If there's a food choice, and we could have pizza. Man, I am so hungry, and I'm on a diet. I can eat this pizza. I'm gonna have a turkey sandwich. Turkey sandwich. Okay, so now how many models are there? 2, 4, 3. 24. 8 times 3, 24. Argument 5 is empty. The gears, yeah, is it making sense now seeing it to be like, okay, it's the amount of combinations. When you look at the original question right here, there's only 3 values of alpha and there's 2 values of lambda. Tell me the math in the chat. Good job, Sweetle, right there. Glad to be on it. Okay, I'm starting to see it. I'm starting to see it right there. 2 times 3. Boom. Got it. So, and there's 2 tuning parameters for the elastic net. Alpha is the degree to which we are pouring in our ridge or lasso. 50-50 is half-half. 0.1 weighs more towards lasso, let's say today. It's one of them. More towards one. It's 90% one, 10% the other. Just look at the formula, but I make my tune grid across all values, so I'll just let it pick, and then I'll look at put in the literature. I'll double check which one it is if someone really wants to know which way I tune towards. Lambda is the amount of weighting penalty we are putting on for regularization. Smallest lambda can be a 0. And yeah, I should memorize which one a 0 alpha is, but one of them. It's either alpha, ridge or lasso. One of them. But it's just, yeah, it's just arbitrary because, I don't know, it's still a model. Eager Giraffe, Captain Gator, Royal Chicken, Amazon Goat, and Diligent Rhino. Great job right here. A true that has a complexity parameter of 0.02 considers or spreading, a tree, and can lower impurity by 0.03. Will it split? So it can lower the impurity by 0.03, and it has a complexity parameter of this. Will it split? Will it split? The complexity parameter is the threshold it needs. It is super duper true. So complexity parameter is how much you need. Does that make sense what complex? Sorry, as I misread it and mistypoed it. Complexity parameter is how much you need the tree to get out of it. The tree will only split if the impurity reduction or the SSE reduction exceeds the complexity parameter. So setting the complexity parameter high is setting a bar very high for the tree to split. So if you set it very high, the tree can't get over that and the tree won't what? A high complexity parameter will lead to a tree that can't what? A high complexity parameter will lead to a tree that can't what? Because you're saying if you split, you must return this much decrease to impurity, putting the groups correctly together, or reduce the sums of squared error. It won't get any bigger. It's hard for a high complexity parameter tree to split, hence you get high complexity parameter trees are more towards the naive. A low complexity parameter says you only need this little amount to split, and then you can split all you want. So if you only need 0.02 to split, and we're getting 0.03 out of our split, yes, the tree will split. Does that make sense for those who got it wrong? Don't worry if you got it wrong, but as I can't even read my own question or type them. But right here, if the complexity parameter is 0.02 and the tree can reduce impurity or sums of squared error, impurity in this instance by 0.03, it will split because it meets the requirement. Next question. The complexity parameter is the amount of reduction in impurity or sums of squared error the tree needs to get to perform a split. If the sums of squared error can be reduced by 2% or the impurity can be reduced by 2%, then the tree will split. Since the impurity can be reduced by 0.03% here, the tree does split. Does that make sense? Because the complexity is the bar, and then what we can do, if we can do more than the bar, the tree splits. And so where we set the bar controls how big the tree grows, because if you set the bar very low, then the tree will find ways to do things that reduce the complexity parameter and grow really big. If you set the complexity, not reduce impurity, I meant to say. If you set the complexity parameter very high, the tree can't make splits that reach this level you're asking it to. I'm like, you can split if you reduce impurity by 30%. And the tree's like, I can't do that. I can't get you that big of a reduction on the impurity. And you're like, well, can't split then. Too bad. Does that make sense? So the tree won't split usually with higher complexity parameters because you're asking it to achieve a very large amount of impurity or sums of squared error reduction, and it won't split. Good questions. And understanding what a complexity parameter is very important. Eager Giraffe, Captain Gator, Royal Chicken, Amazon Goat, Stellar Bunny. We have t-shirts for everyone to first place. First place gets a $20 gift card to Amazon or Starbucks, your choice. Make sure to email me from your UTK email. Next question, the highest value of Gini coefficient is 5. I have the last few fun ones here. Finishing off, I'm gonna take a break and relax afterwards. Turkey sandwich, maybe protein milkshake and some snacks, some Ring Fitness, a new video game. This is false. The highest Gini coefficient is technically 1, but that would require infinite groups. The Gini coefficient approaches 1, its amount of impurity, and highest Gini is 1. So it approaches 1, really can't be obtained unless you had infinite groups, so theoretically 1, but usually like 0.9. For us, with 2 groups, the highest Gini is 0.5, mentioned earlier. Last question of the day here. Here we go with Eager Giraffe, Captain Gator, Royal Chicken, Stellar Bunny, and Diligent Rhino. Here we go. Which of the following explains what the validation portion of our data does? I love it to end. Rocket League and Stats Night do it. I'm shocked I didn't get into Rocket League. I was so close. Like, I should play this. And I was like, I got other games. I bet I would have played it. Good job. Now, how do we investigate overfitting? How do we investigate overfitting? Investigating overfitting is done by seeing if our data what's what on the what's. Investigating overfitting is by seeing if our data what's what on the what. To see if our data works well on the holdout is to investigate overfitting. What do we use to estimate the model? That is going to be the trained data. The trained data is how we estimate model estimates, which the validation is a subset of it, so it's kind of part of that, but not really. Find the generalization error is going to be the holdout. The estimate of the generalization error is from the validation because it's how we think it will do. With that, the winners on this 4+ hour stream today are going to be Eager Giraffe with over 12,000 points, Captain Gator, and Royal Chicken. Eager Giraffe, please email me. Everyone else, we got t-shirts for you. Please let me know. Might be around the office Tuesday. Swing by or next semester and say, hey, Brian, I should have these t-shirts. And we might have your size in because we're running out of t-shirts. Thank you to Kahoot. Eager Giraffe popped off right there. If you want to say you are in the chat, I want to say a huge thank you. It's been a big day. I'm going to go back and relax here. But thank you, everyone, for being here, saving this. Big day, 4-hour plus review, 4-hour and 20-minute review right there. I'm gonna go back and I haven't been coughing that much. I'm happy because like earlier this week I was coughing a whole bunch. And you notice I almost kind of sound normal and I haven't had to clear my voice as much. I'm really happy about that. So luckily in better health. Only shave, got all rough right here. Get a haircut, shave. I was gonna get a haircut and then I got sick and I was like, well, I don't want to go to the barber and be like, hey, coughing, sorry. Sir Bad Steve, good job right there. Brent, good job. Jeremy, good job. Emma, good job. If I can sleep tonight without coughing, that'd be amazing. Amazing. Meat, good job right there. Matthew, good job. Thank you, everybody. Eager Giraffe, please help the boys right there. The Boys Season 4, is it now available on Amazon? The Boys Season 4, find out what happens to... I won't even say any character names because I don't want you to know who's in what season if you've never seen it. Because you never know what's going to happen on a show like that. No spoilers. Find out what happens to the boys on The Boys, which is not always all boys on The Boys. Good show. Can't wait to catch up on it. Probably watch over break. Watch some Invincible, The Boys, got a lot of stuff, and play some Hyrule Warriors Age of Calamity. With that, it's time to go. Bye for now, everyone. Bye. Doesn't season 4 come out in a few months? I bet it does. I just saw the trailer, right? But I don't even know what happens.